So has anybody got any questions from yesterday? Any comments on how practice tests are going or anything like that? Anybody feel like gouging their eyes out? We have a lot to cover today, but rest assured, the harder stuff was yesterday. Even if it wasn't, I would say that anyway, just so you'd feel better about it. So you'll just have to take my word for it. Today is what I consider more of a systems and rules day, which is why it's only 4 hours. And you know, we spent a lot of time on math and theory, and I think a lot of people who go into ham radio don't really like, you know, they don't really want to do the math and theory, but the math and theory helps explain everything else. So even if you've been exposed to it, even if you're not an expert, it helps a lot to understand things. At least that's my belief. So. All right, 1 minute to class.
I noticed that the video wasn't posted on your YouTube.
I sent everybody a link and it should be up. So did you check?
I got the link in email and I was able to see
Yeah.
the video.
I have received the link as well.
Good. So yeah, if I didn't just post it, I posted it so that, you know, there was, it wasn't accessible to just anybody. You actually had to have the link for it.
Okay, I see it now.
Okay, good. Okay, it's 10 o'clock and that means it's time to go. And I saw that there was a minion here. That's fine, although minions might have hard time taking the exam. All right, so we are on to digital modes, packet and stuff like that. We're on page 65 of the manual. And yes, we do have to get all the way into the 120s. So we have our work cut out for us, but that's okay. Okay, so digital. Digital is basically just ones and zeros instead of analog, which is like voice, where you have values that are anywhere between, let's say 0 and 1. You could have a half or a third or 7/10 or 0.924865. Digital is basically just 1 or 0. So when a signal gets there, it's either a 1 or a 0. That gives us some benefits, such as, well, if it's 0.7 when it gets there, and we know that it's either a 1 or a 0, it was probably a 1. If we get a 0.2, we know it was probably a 0. So digital gives us the ability to do all kinds of cool things. Like if we know that it was one of those, we can do error correction by taking extra bits, extra values, and sending it along. We can have voting systems that take 3 copies. If we get 2 of one and 1 of the other, we're going to go with the majority rules and say that it was the one that had the 2 of something. So there are a lot of digital modes out there that we use. There's not just like a digital mode. So in some examples of digital modes, we've got 802.11, which is the IEEE standard that we use for Wi-Fi. There's an N and a B and a G, and probably some others now as well. Packet radio. If you turn on a radio and listen to 144.39 megahertz, you'll hear packets going across the network. That's basically a digipeater frequency that allows store and forward messaging to occur from point to point to point to point. So you can address a message and it basically gets handed off from station to station until it gets to where it's supposed to go. And there's also something called FT8. FT8 is a multi-tone frequency shift keying system where you basically have one of 8 different notes, well, if you can think of them as musical notes, and they kind of like make a little player piano pattern on the screen if you look at it in time. And that translates to a particular letter or code. And then you take a whole bunch of them put together and it translates to a whole message. What's included in a packet radio transmission? You have a checksum, you have a header, and you have an automatic repeat request. So basically, let's say that I'm sending a message to Chris because I can see Chris's face on my screen. And I say, Chris, your message is 62884. And Chris says, I didn't get it. Send it again. That's an automatic repeat request saying, I didn't get it. There's a header, which basically says, I'm sending this to Chris, which means that it won't go to Raul and it won't go to Magnus. It'll just go to Chris. That's the addressing information. Kind of like on an envelope. That's the postage, that's the postal address. And finally, a checksum. That basically says the message was 62448, and the total sum of all of those is 6 and 2 is 8, and 4 and 4 is 8, and 8, that's 24. So 62448 and 24. Well, if you got 25, that means that something was wrong, and you'll say, I didn't get it, send it again. That's a checksum. ARQ is an error correction method in which Chris can say, I didn't get it, please send it again automatically. APRS is the automated packet reporting system. Basically, if you think of all these pieces of information as locations and data and things like that, I'm now sharing an APRS map. Notice that we have a lot of different stations. We have home addresses. Everything that you see on this map is an automated packet reporting station that has information that ties it to a physical location through a GPS. And it's then uploaded eventually to a website in Finland, which is aprs.fi. And notice that there are a lot of them, even in areas that we don't usually think of as being overly populated. There are still a lot of them because there are hams all over the place. So Seattle's going to be just full of them, of course. And so basically any station that you see here, here's a weather station. Sometimes you'll see a car with a trail attached to it. Like here's a bunch of dots that says Elizabeth Ann, and it shows that it's a boat. So somebody is a ham and has a packet station on their boat. That's indicating where it is. There's the boat information, KB7RYY, and how fast it's been moving and in what direction. So we use this for real-time telemetry. You can actually hook a packet transmitter that weighs about 8 grams to a helium balloon and float it up in the air with a small antenna and a small antenna and a solar cell, and it'll transmit at let's say 100 milliwatts from 30,000 feet. And that signal can be picked up for 100 miles in all directions. So basically it's saying, here I am, here I am, here I am. And it's your balloon is floating through the sky. Maybe it's going overseas. Maybe it's just going over North America. It's basically beaconing its speed, altitude, temperature to the ground. And it's really cool for scientific experiments. Kind of data that can be transmitted via APRS. You have GPS, text messages, and weather data. PSK stands for phase shift keying. So yesterday we were talking about FM and phase shift. So let's say that I have a signal that in time looks like this. Just a good old sine wave. But then it gets to this point and it goes like this. Right there, it should have gone all the way down and back up. So this gap right in here is a phase shift. So by indicating whether or not that's 180 degrees or 45 degrees or 90 degrees or 135, that basically determines whether or not it was a 1, or, well, in some cases it could be a 0-1 or a 1-0 or a 1-1, or it could be a 0-0-1 or a 0-1-0 or a 0-1-1, et cetera, all the way up to 1-1-1. So this is a way of encoding data. It can be a different number of bits at a time, just by seeing what the phase shift was. And this is known, again, this is known as PSK, or phase shift keying. And we can do quadrature, we can do 8 PSK. And again, like quadrature would be 90 degrees at a time. Binary would be 0 or 180 phase shift. 8 PSK would be 45 degrees at a time, because there are 8 different 45-degree segments in one full circle. So depending on which way you do that, you can encode a different number of bits at a time. DMR is digital mobile radio, and we are on page 66. Digital mobile radio is a technique for time multiplexing 2 digital voice signals on one single 12.5 kilohertz repeater channel. So there's a couple of different ways to look at this. Okay, so we have our frequency spectrum, and we have, let's say, 12.5 kilohertz. So that's 12,500 hertz. There's a couple of different ways to do this. We can split it so that channel 1 is the lower channel and channel 2 is the upper channel. Or the problem with that, of course, is that each of them loses fidelity. They're both working at the same time. The other way to do it is to say, over a period of time, this time slice is channel 1 and this time slice is channel 2, and then 1 and then 2. As time advances, they keep alternating back and forth. Digital radio, which is basically digitized voice, doesn't have a requirement to operate full time to get full fidelity. So what you basically do is you split the channel in time. And this is basically called time division multiplexing, where each of the channels gets to operate for a specific period of time. Now, each of the radios that's programmed to operate on that channel has to know that I am on channel 1. Because of that, if it's done properly, you will not even know that you're sharing it with channel 2, and vice versa. But if the time synchronization isn't there, then you'll hear just noise and static, and you won't hear what you're expecting to hear. Which of the following operating activities is supported by digital mode software in WSJTX? Okay, so we're going to put up a guy here, and let's see. If I can find it. There we go. Okay, let's share it. So this person, notice it's Joseph H. Taylor Jr. of Princeton, New Jersey. So his initials are JT, Joe Taylor. And we have this piece of software, which is called WSJTX, which is Weak Signal Joe Taylor. So Joe Taylor is the inventor of all the JT modes, which includes FT8. It includes JT65. There's a high-speed meteor scatter mode that's a part of it. He basically came up with a new encoding scheme. So if you think for some reason that radio is dead, the next time you grab your phone, realize that it's running a really high-speed modem, basically using some encoding scheme that somebody came up with. And we are still coming up with encoding schemes that are new. So let's say that I look up Joseph Taylor. Joseph Hooton Taylor. Oh, look, American astrophysicist. Oh, look, there he is. Well, it turns out that on the air, he's just Joe. But if you look up who he actually is, he's a Nobel Prize winning astrophysicist who happens to teach at Princeton University and happens to be a ham in his free time. And part of that is that he came up with this really cool method of encoding and decoding data because he really likes to do moon bounce. Moon bounce is the act of sending signals off the moon, bouncing them off the moon and having somebody receive them. By the time it gets back to Earth, they're really, really, really weak. So what he did is he created a mode that was really good, very, very low data rate, but really good for weak signals like that which you would receive bouncing off the moon. And it turns out on top of that, it's really good for terrestrial use too. And it's pretty much taken the ham radio world by storm. Like, for instance, I can operate from inside a hotel room using that mode with my antenna inside a metal hotel room and still be able to make contacts. So weak signal propagation beacons, meteor scatter, and Earth, Moon, Earth are parts of the JT software package. FT8 is a digital mode capable of low signal to noise operation. That is, in addition to, let's say, Morse code, FT8 is one of the best signal modes for operating at low power. An amateur radio mesh network. Okay, so a mesh network is, if you think of a network has a bunch of points on it. Each of them has an address. A mesh network basically is a network that is self-healing and non-deterministic, where a message that starts here and that is targeted to go here, it does not have a set path to get the network to get the message through the network. There's no guarantee that if it made it that route once, it's not going to go this way the next time. The reason that this is helpful is because let's say that something happens to that network and this section of the network is no longer available. And then something else happens and this section of the network is no longer available. It will basically seek out additional stations and find a new route to get to the endpoint. And that's mesh networking. It's a self-healing network. And what the other thing that's cool about it is that this actually uses standard Wi-Fi hardware because Wi-Fi hardware operates at 2.4 gigahertz. That actually is the same frequencies as we have ham frequencies on, except that, again, we're not allowed to communicate with them and they're not allowed to communicate with us. But if we put new firmware in a router, we can basically turn it into a ham radio. And we can actually program it to behave in this way, whereas a standard Wi-Fi router would never behave in this way. Okay, we're now on to electrical safety. We're going to go through this pretty quick because most of it is common sense just to keep you from electrocuting yourself.
I have a question, Scott.
Yes.
Is CW digital?
It is a form of a digital mode, yes.
Okay. Thank
It's
you.
easiest to think of as a digital mode.
Thanks.
Because something is either there or it's not there. Now, but it's not Morse code actually, because there are two elements. There's absence of a signal, and then there's a short, which is a dit, and a long, which is a da. It actually is like, it's a digital code, but it actually has 3 different values, not 2. So something's there, but you have to determine whether it's a short burst or a long burst. So, but yes, it is a form of a digital code. Okay, health hazard presented by current flowing through the body. It can heat your tissue up. If anyone's ever gotten a good shock at high voltage, high current, it leaves an entrance and an exit wound where it jumps out. It can disrupt the electrical function of cells because we are basically an electrical machine. And it can cause involuntary muscle contractions. I once got a 250 volt DC shock from a radio when I was 10 years old. My arm started here and it ended up here, and I had no idea how it got there. In the United States, we have 3 wires on our standard 120 volt circuits. There's black, there's white, and there's green. Green is always ground. It's easy to remember. Green, ground. White is the neutral and black is the hot. This is not true in other countries. So if you happen to live in another country, you have to check and see before you actually start messing around with the house wiring. But in the United States, the hot wire is the black wire. A good way to guard against electrical shock, use 3 wire cords, which basically have a hot and a neutral and the round plug, which is the ground. All AC powered station equipment goes to a common safety ground and put in mechanical interlocks whenever you have a high voltage circuit, like an amplifier, and don't disable the interlock. One thing we're going to get into is the difference between safety ground and RF ground. They are different things. So remember we said that ground is ground. Ground is not always ground. Okay, the purpose of a fuse in an electrical circuit is to prevent to remove power in case of an overload, in particular, an overcurrent situation. A 5 amp fuse, if it suddenly is required to handle 12 amps, is going to blow really fast, protecting everything downstream. You also, in your breaker panel, have a circuit breaker. A circuit breaker is basically a resettable version of a fuse. Where should a fuse or circuit breaker be installed in a 120 volt power circuit? You put it in series with the hot conductor. And what color is the hot wire? We saw black. Yes,
Black.
the hot wire is black. Okay, why should a 5 amp fuse never be replaced with a 20 amp fuse?
To catch fire.
Unless you know what you're doing, unless you were the designer and you know it's okay. The reason being that if there was a 5 amp fuse and it was designed properly, the circuit was designed properly, and the 5 amp fuse blew for some reason, there's probably a reason for it. Yes, the right foot does balance everything. What hazard exists in a power supply immediately after turning it off? Okay, so inductors, the magnetic field will dissipate. A capacitor, if you charge it up, will stay charged for potentially a very, very long time. A television tube, the old school TV tube, which was a cathode ray tube, which looks like this, had one plate and another plate. And that actually would be charged up to about 20 kV, which is 20,000 volts. So somebody every so often would go find an old TV tube and start doing something with it and get a 20,000 volt shock, which would definitely wake them up. My father once, when I was a little kid, gave me a computer power supply capacitor. I'm not sure why he did, other than the fact that he was an electrical engineer and he thought that I'd think it was cool. And it said 500,000 picofarads, or sorry, microfarads, which is a half a farad, but it was only rated 5 volts. Okay, well, that's no big deal. Well, so I took this and I hooked up a battery to it like this, and I went like that. But okay, well, I'll charge it up. And this was a 9 volt battery. Well, it didn't blow it up. It could handle 9 volts. Well, then I charged it up, and that was really boring. I took a voltmeter and it measured 9 volts. I'm like, oh, how cool. Okay, well, I guess I'd better discharge it. All right, I want somebody to unmute themselves as soon as I start telling them this and to tell me what happened. I said, I better discharge it. I took a screwdriver over here, and I took another screwdriver and stuck it over here. Don't somebody tell me what happened.
Arc.
Yeah, yeah. And what happened?
It blew.
I ended up with a bright blue flash right there where they touched. And is anyone familiar with an alloy called this? Anyone familiar with that? Chrome vanadium steel?
Is that CRV?
Yeah.
Weld them together.
It actually almost welded them together. When I looked at the screwdriver, each of them looked like this with like a pit. that was removed. That it was hot enough that if I hadn't pulled them apart, they actually would have welded together right there. So when I was 10 years old, I discovered the magic of arc welding. And it only took 9 volts. So what did we learn about that? It's not the voltage, it's the current.
So help me understand that 9 volts, that's a little bitty, that's nothing.
Nope.
But it was enough to weld.
It was a lot of charge. It was a
Yeah.
lot of electrons. I mean, that was probably 1,000 amps for a really short time. Anyone do arc welding? Does anyone do arc welding here?
I've
Yeah.
done a little bit of
Yes.
tailoring.
Okay, how much current do you normally set your arc welder for?
Depends on the material.
All right, let's say just steel to steel, mild steel.
I haven't worked with mild steel in a while. Last material I worked with was aluminum.
Okay, well, let's go with that. What do you set
Yeah.
your current to?
Oh geez.
Couple hundred
Uh,
amps?
Yeah,
Okay,
It's
so this
somewhere
was
around there.
a couple hundred amps is enough to weld aluminum. I would think that steel is probably 300 amps maybe. So for a very short time, there was enough current there coming out of that one capacitor, which was charged by a 9-volt battery. It took a little while to charge it. It didn't take very long to discharge it. So, yeah. So charge stored in filter capacitors can cause a very nasty low voltage shock.
Is this the same concept behind, you can't use the car battery to operate home appliance, right?
Well, I mean, you can if you use it through an inverter. I mean, a car battery is 12 volts.
But how much is the current?
Well, it depends. I mean, if you run it through an inverter, it'll pull as much as you need. I mean, if you run a car battery, a 12-volt car battery through an inverter and generate 120 volts AC out of it, sure, it'll work. I mean, people do it. But you have to look at how much current. Okay, so let's say that you're running this battery through an inverter, which is putting out 120 VAC, and you're running a microwave oven, which is 120 volts at 10 amps. How many watts is that? Everybody?
1200.
1200 watts. Okay. And your input voltage is 12 volts. How much current do you need to make that? By Ohm's law. You need 100 amps. So your inverter has to be a good solid 1200 watt inverter and your wiring has to be capable of handling 100 amps, which is basically like a number 2, maybe a number 1, maybe a 1/0. It's big fat wire.
What is the, so the maximum amps that is coming out of a 12 volts battery is determined by the load.
Yep. And if you have a big battery, let's say you have a bank of batteries. Yeah, no problem. If you have a single car battery and you try to pull 100 amps out of it. So a car battery, they're rated in cold cranking amps. Let's say you have a battery that's rated 600 cold cranking amps. That's at 600 amps for a very, very short time, like a few seconds. Usually a storage battery is rated in something called an ampere hour, which basically means that it can deliver a certain amount of amps for a certain amount of time. So this battery might have a capacity of 200 ampere hours, which means it can deliver, let's say 20 amps for 10 hours or 10 amps for 20 hours. And it's not exactly as simple as that, because if you try to deliver 200 amps for 1 hour, the battery's probably not going to be very happy with that. It'll have a maximum discharge rate. So you have to look at what your battery capacity is. And that's just basically based on size, physical size. The number of atoms in the battery determines that.
Sounds good. Thank you.
Which of the following is a safety hazard of a 12-volt storage battery? If you short it, shorting it is basically a rapid discharge, can generate a lot of heat. Right? And that heat can cause the battery to go kaboom. This happens with car batteries that short out. Because what ends up happening is you generate a lot of heat. The rapid dissociation inside, because it has acid, generates hydrogen gas. Heat and hydrogen gas, anyone?
Explosion.
Explosion. And then a shower of sulfuric acid. Bad idea. Which can be what can happen if you charge or discharge a battery too quickly, overheating or outgassing. And again, it's hydrogen gas. Okay, we're on to antenna and tower safety. When putting up an antenna tower, watch out for electrical wires overhead. Even if you don't know exactly what they are, assume that they are high voltage. I once had a demonstration when I was at the Dayton Hamvention in Ohio. Dayton Power and Light came in and they did their traditional high voltage safety demonstration. They basically took a dry piece of rope and they brought in a 7,200 volt line, and they had a grappling stick made of fiberglass, so the guy could put something up there without killing himself. You know, even so, he had the big rubber gloves on and big boots and a helmet and face shield. And he put the rope up there and nothing happened. Well, then he took the rope and soaked it in water, and he put the bottom of the rope in a bucket of water. And then he took the top of the rope and dropped it onto the power line, and like a 1-inch thick rope completely disappeared with a flash. Just disappeared into thin air. That was basically simulating a person. So, you know, the power lines overhead, they're typically not going to be 120 volts. Even if they are, you should stay away from them. Typically, the big ones are going to be 7,200 volts, 12,000 volts. They'll, you know, it'll ruin your day. The minimum safe distance from a power line when installing an antenna is enough so that if the antenna falls, nothing can come within 10 feet of the power line. Power likes to arc from place to place through space. You should also position the antenna so no one can touch it while transmitting. If you touch an antenna that is operating, you can get an RF burn. I once actually did this to myself by grabbing a handheld radio and transmitting with it, and I had a sweaty hand, and the back of the radio had a screw on it, and my hand, because when I was transmitting, my hand was sweaty, it would occasionally make and break with the screw. Every time it did that, it made a little bit of an arc. Now, to understand why, what I'm going to do is show you a quarter wave antenna. And I don't know why this keeps doing that. There's a quarter wave antenna, and here's a radio. Okay, what part of the antenna is missing, everybody? Based on what we learned yesterday, what part of the antenna is missing?
Is it grounded?
The ground plane, right? Normally you'd have a ground plane. Okay, but now let's take this antenna and we're going to put somebody's hand around it. There's somebody's fingers. They have 4 fingers on their hand. Okay. Where's the ground plane?
Your hand, your arm.
Your hand. You are capacitively coupled. You are actually the ground plane. Now let's say that there's a screw right there that is making and breaking.
This is a handy talkie that we're holding?
Yep.
Okay.
So let's say on this handy talkie that there's a little screw on it that is making and breaking with the skin on your hand, and you're all sweaty. So it goes from being capacitive, which is no contact, to actually making contact. So it's jumping back and forth. I actually got an RF burn on my hand because of the constant arcing back and forth whenever it made or broke contact.
Friend of mine has a bow fang, and apparently on the back side of the bow fang is a little metal tab.
Yep.
That you put your wrist
That's right.
holder
The belt clip.
on.
The belt clip and the wrist. Yeah, that's what it was.
And that's exactly what happened to his hand. It got so hot, he ended up taking the back off, removing that little metal clip. And that's exactly what you're describing.
And if you're running at low power, typically you're not going to feel it. But if you're running at high power, you have more RF current. You're more significant. Let's see what's required when climbing an antenna tower. Wear a hard hat. Wear a climbing harness. Tie off to the tower. Don't say, well, I'm just going to get around these guy lines and disconnect completely. That's why most climbing harnesses have 2 loops, so that when you get up to a certain point, you disconnect one and you reattach it, and then you disconnect the other one. If you're 50 feet in the air and you completely disconnect from it and you get stung by a bee, you're probably going to hit the ground. And it's not the fall that hurts you, it's the impact. So, and have sufficient training on safe tower climbing techniques. If you're on the ground, make sure you wear a hard hat, make sure you wear safety glasses, because somebody's invariably going to drop something. Now, I've also done tower work back in my younger days when it was 20 degrees outside. And you know what happens when it's 20 degrees outside? Your hands don't work very well. That metal is really cold. And if you wear gloves, you can't grip anything very well. So everything's cold and you are guaranteed to drop something. So people sometimes will actually take their tools and they'll use a rope on the tool and lash it to themselves. So if they drop it, it doesn't end up hitting the ground. And then they don't have to go down and chase it or have somebody haul it back up. When is it safe to climb a tower without a helper or observer? The answer is never.
Never.
When using a crank up towers are not designed when they're cranked up without mechanical safety locks. The idea behind a crank up tower is that you crank it and it goes up. It's designed to hold an antenna. It's not designed to hold a U. So unless you have mechanical locks in place or it's fully retracted, do not climb a retracting tower. A safety wire through a turnbuckle. Okay, so for those of you who've ever worked on a tower, we talked about guys yesterday. So a guy system is basically 3 lines usually, and they're tensioned. Well, usually what we'll end up doing is taking two different guy lines and connecting them at a turnbuckle. Now we also put a wire through the turnbuckle. The reason that we do this is that a wire that is being exposed to a tower, that's connected to a tower and exposed to the wind will vibrate. And anything that vibrates, if it can either get tighter or get looser, if it's threaded, is going to get looser, which means that it's going to slack your line. So if you get one line that slacks more than the other line on your tower, guess what happens to your tower? Your tower starts to tip over.
Sway, yeah.
And then it'll break because a tower is not strong enough to hold itself up. It needs to be guyed to make sure that it's got adequate support to hold itself up at multiple places. And the higher it is, the more supports it needs. So it's important to tension all these lines. So a safety wire through a turnbuckle will keep it from loosening up in the wind.
It's also important to make sure that you don't have them too tight going up, because there's been a few times for some soldiers and I would set up like a 15-meter mast. And we'd have some of the guy wires too tight and they would snap as we went up.
Yeah, exactly. If you end up with an imbalance, you can actually, you can also tighten them too much, in which case you'll snap something. And I mean, like for a temporary setup on field day, we use ropes, and a rope is good enough for a temporary setup. If you're doing something permanent, you're typically using a much heavier gauge steel wire. And if you're going up on the tower, you got to keep checking those guy wires because they don't last forever. They corrode, they get tensioned and they break. It even happens on bridges. They go up and they check all the bridge supports every so often because, stuff doesn't last forever. Which of the following establishes grounding requirements for amateur radio tower or antennas? That's your local electrical code. So whenever you put up a tower, you got to check with your local authority having jurisdiction and figure out what they require. The overarching standard is the National Electrical Code, but then your local codes kind of like work on top of that. Proper grounding method for a tower. We use 8-foot ground rods, one for each tower leg bonded to the tower and each other. And this is for lightning protection. Which of the following is good practice when installing ground wires for lightning protection? You want to make sure that all connections are short and direct. The other thing is that lightning does not like to go around corners. So if you have a ground wire that looks like that, what'll happen is that if you do get a lightning strike, it'll go like this and it'll jump to the ground or to something else. It will not follow that. It will not follow that wire. Lightning does not like to stay in. The lightning doesn't like to go around bends. What should be done to all external ground rods or earth connections? You should bond them together with a heavy wire or conductive strap. Where should a lightning arrestor be installed in a coaxial feed line? On a grounded panel near where feed lines enter the building. Okay, so this is a drawing as well. So here's my tower. And here are my antennas. And here's another one. And I have feed lines coming down from each antenna, and they come into my station. Okay, so let's say that my tower is grounded. But my antennas obviously cannot be, because if they were grounded, that wouldn't work. And I have a direct lightning strike on one of my antennas. Coming down the center of the cable is all that energy inside my cable. What happens if that makes it to my radio?
Buy a new one.
You buy a new one, yes, if it doesn't set the inside of your building on fire. So what you would do at that point is, here's the cable coming in. You have a tube which is filled with, there's your center conductor. It's filled with a gas that is typically not ionized at normal voltages. But when it gets a lightning strike, what happens is that the tube becomes ionized. The gas in the tube gets ionized and becomes conductive. Then the outside of the tube is then connected to ground. So now you have this wire on the inside, and it's being surrounded by a conductive gas. And hopefully, if you're lucky, your lightning strike will come down, ionize the gas, and send it to ground. So you take all of your lightning protectors and you tie them all to a common plate. So you might have 6 of these, and then tie all of those to ground. Now, what's the most important thing you can do if you know there's a thunderstorm coming, for those of you on the East Coast? Disconnect your radios. That's right. That's really the best way to make sure it doesn't get blown up. Okay, so now we're into RF hazards and radiation exposure. But before we do that, I am going to say, JD. Take it away, JD. Hello, JD.
There we go. Had to get rid of the banner there. Yes, Scott. Good
Take it away.
afternoon.
Give your brief spiel.
What brief spiel?
You've got a brief spiel
Yeah,
about
okay.
examinations, and if there's
I'm JD, and I'll be running a session this afternoon for the testing of y'all, and hope you all pass very nicely. I'm located in Maryland. I don't freeze in Alaska. I did that for 6 years, a long time ago. Got smart and left. And
uh-oh. Did JD freeze up? Or did I freeze up?
Now me. Good old Comcast. I got your note on Chris. What about Greg Hudgens?
I think Greg was going to reschedule. Is that right? Greg, are you here?
Correct. I was going to reschedule.
So there you go,
so I
JD.
can take him off too. So we got 16, I believe it is for the time. Yeah, Scott will be the gate guard. He'll call each one of you when it's your turn to come into the room. We'll give you a brief spill when you come into the main room. We'll rename your 2 devices to be something like your name, Seth Swan primary, Seth Swan secondary. That way, when we tape it, we know which device that was. And when a room comes available, we'll move you into that room. There will be 3 people in it. I'll lead in 2 at least. And they will test you, tell you how they'd like to have that second camera positioned so they can see what's going on. And the whole thing takes maybe 25 minutes if you have studied well, maybe 30 minutes if you haven't.
So let me ask a question. Is there anybody who absolutely needs to go first? Because we can't take everybody at the same time.
Correct. We'll be bringing you in between 3 and 5 minutes apart.
And if you're on the East Coast, I can see that. So who was early? Raul? All right. If there's anybody else who wants to go early, let us know. Now's the time. If there's anybody else who absolutely has to go late because they have something going on, that's another good thing to know.
I can go whenever.
Who else? Lucas goes early. Okay.
I can go late.
Okay. I can't see everybody at the same time. Who was that?
Chris Holden, I can go late if need be.
Chris Holden, I had a question about you too. Your registration showed up with 4 names. Have you got 2 middle names?
Yes, I do.
Okay.
It drove me nuts. Now I got the other question I had was the name that showed up on your payment was Brian Wendell. Who's he?
Oh, that might have been a fat finger. That's yeah, that's not correct.
So it should be your name, right?
Yeah,
I'll
yeah.
take care of it.
Thank
Okay.
you.
And
Now
the
I won't be so
question,
crazy.
there was another question. Is it just for the East Coast right now? No, it's for everybody. And I like JD said, I'm going to be the gatekeeper. I'm going to be, if I don't, if you're taking a test and I don't have a good phone number for you, I will have trouble getting a hold of you. So it's a good time to tell me what a good phone number is for me to call you on so that we can, and don't screen your call.
It does make it
So
a little difficult.
it does make it a little bit hard. But I will do my best to make sure that everybody gets in. And like I said, if anybody needs to go early or needs to go late, remembering that we've got multiple time zones at play here, now is the time to say so.
I wouldn't mind going earlier if that's okay. I'm Joe
Yep.
Lewis.
Okay.
I'm on the East Coast, so I got dinner to get to.
Okay.
Thanks.
I got you on the list. So we got Raul, Lucas, and Joe going early and Chris Holden going late.
I can go whenever.
Okay. So everybody else, it sounds like, can go whenever, but Travis said earlier if possible. Okay.
Okay. Has anybody got any questions?
Just so you know, the exam is 35 questions. We'll make sure you get the easy one. By the way, there is no easy or hard one. All the tests are randomly generated from the question pool. If you've been studying and you've seen all the questions, that's all the questions. You can't get asked anything that is like a surprise because that doesn't exist.
There's 35 questions. Like Scott said, you need 26 to pass.
Yep.
If you get 24, we can give you a second chance.
If you also get 35 out of 35 and
Scott will
there's
buy you
time.
a steak.
Yeah. Well, but there's also, if you ask very nicely and we're doing okay on time, JD may say, hey, do you want to try the general exam? Again, it's time permitting because we have a pretty big group, but
Actually, we'll leave that up to the lead in the room to do that.
Okay.
All I'm going to do is bring you into the main room after Scott gets you there, and we'll do the preliminaries. Make sure both cameras are there. Make sure you're named the way it should be. Feel out for any questions you might have. When a room comes open, we'll send you in there. Hopefully you won't be nervous and you'll go right to town and y'all come up with the aces.
Yep. And if they pass, they will get into the database tomorrow, right? And then they'll get it. Will they get a note from the FCC saying
As
pay
soon as
up?
it gets in the database, hopefully about 8 o'clock tomorrow morning Eastern time up at Gettysburg. And once that's in there, very shortly thereafter, I'd say within an hour, you'll have an email that says, congratulations, you passed, you owe me $35. The sooner you pay that thing, that fee, the sooner you'll get your call sign. Use your laptop to do that payment to the FCC. They haven't figured out how to make a tablet or a phone work with the payment system.
JD, you've got quite the setup there. Is that an FL 2100 in the background?
That's an FL 3100,
3100.
2100.
2100. Okay.
And I got a 30L on the other side.
Is that the
And I
one with
get-
the five? Is that the one with the 572Bs in it?
21?
Yeah.
Yeah.
Any trouble finding those these days?
DX Engineering has them for a match set at $185, I think it was.
Oh, that's cheap. And they're
Yeah.
decent. They finally find a good supplier.
Don't know. I haven't bought a pair yet.
And I like that 830 on the shelf, the TS 830.
That's a nice little radio.
Those were nice. I mean,
My 2 favorite radios is the 430 and the 830.
yeah, the 830 is one of those things that the audio I always thought was just beautiful on that.
Let me turn turn the lights on here so everybody can see the mess that I got in this thing I call a ham shack.
That's a beautiful mess.
And to give you a little background, I got into amateur radio when I was 14 years old, 1962. I'm 75 now. You figure it out.
Yep.
That's what you see in the background.
Well,
61.
we started at about the same age, but you had a little bit of a head start on me. So.
And after I retired from the military 30 some odd years ago, I started building a ham shack. And of course, it got a little out of hand on me. So I hope I never have to leave this house.
So here's a morbid question. Have you started creating an exit plan for in case something happens, what to do with all this stuff?
It's in my will that my daughter will get rid of this stuff, but I don't think she's going to appreciate that.
You know, because we've actually had that discussion at some of our meetings.
Yes, you need to make a plan. And what I'm thinking about doing is changing my will and give it to one of the local radio clubs I belong to and say, here you go. Take care of the new guys. If they want this stuff, go at it. Otherwise,
keep sell what you don't want, keep the money.
Exactly.
Yeah.
And that's one of the things I do on the side is estate sales. I just handled one for a guy, WA3WIX, who died about 3 years ago. His son-in-law called me one day and said, I need help. I don't know what to do with this stuff. Can you come over here and help me decide what to do? Well, I went over there and he had 100 feet of Roan 45 standing in the air with a big 5-element model bander.
Somebody's got to take it down.
Somebody's got to take it down, and he's in his room, in his shack. He almost had as much stuff as I had, except he had something that was even better. He had some linears like the Henry K and the Alpha 78, and I drooled on both of them. And I started advertising the stuff, and I wasn't getting very far. And he says, "I tell you what, if you buy all this for $2,000, we'll call it even."
You just got to haul it away.
Just hauled it away. So, and the tower, I couldn't take it down because I don't have the equipment to do it. I had a friend that worked for a crane company that had a 100-foot arm on it, a boom on it. I said, hey, Jack, can you bring that crane over here? Let's take this tower down and maybe we can repurpose it somewhere else, maybe up over a bar stove for one of the repeaters.
He said that was Roan 45?
45.
Ooh, the good stuff.
It is heavy duty stuff. And he said, no, can't do that. People who owned the company before, where we had the ability to do that, where we could write off the stuff as, what do you call it? Public service, sold the company.
Oh.
And they don't like, the new company doesn't like that. So here I am stuck with 45.
Aw.
And
all right.
Well, I'm not sure what I'm going to do with this. And the guy says, give me recommendations. So I sent him to some guy in Delaware who takes down towers. His idea was to just cut the feet out from under it and let it fall. And that's what he did.
Yeah, that's too bad. All right. Well, anyone else with any questions for JD before we go back? And Abu, a lot. The question was, how much did you invest on that setup? You don't want to know.
I ain't got an idea.
There's an old joke about don't let my widow sell this stuff for what I told her I paid for it.
Well, unfortunately, this is my third wife, so she doesn't know. We'll let it go.
So the other thing is, if you ask the question, how many radios does one person need? The answer is, okay, there's X, which is how many I have. I need X plus one. So,
or a friend of mine down the street says, there ain't no such thing as too many radios.
Yeah.
All right, y'all. We'll see you along about 5 o'clock in Scat.
Well, your time.
2
o'clock Pacific.
Yeah, Maryland time. That's
all right.
5
Thanks,
o'clock
JD.
Eastern time, whatever it is on the West
Scott,
Coast.
I'm
Yeah.
sorry, I have a question. We lost our internet twice right while you were talking, so I missed about the last 5 minutes or so. I got from when you were saying that if, let's say you got a 24 out of 26 and you just, you know, you didn't pass the
If you get
test.
24 out of 26, they'll probably let you go again.
Right, and then you had said something right after that.
Oh, if you blow it away and you get 100%, depending on how busy the room is, they'll probably let you, they'll likely say, hey, you know, you aced this. Do you feel like trying the general?
Oh.
I don't know, Scott. I heard something about a
gotcha.
steak.
What was it? 2 classes ago, we had a guy try the technician and he blew it away and he took general and he missed by 1. He said, well, let's take the extra 2 just for ha-has. And he made it.
I actually had somebody from Portland State who is an electrical engineering student, and he crushed the tech, and then he did well on the general, and then he passed the extra too. He said, I've never really looked at it, but yeah, that was kind of my plan. So yes, it was Cesar. Yes. All right, back
Yeah,
to
matter of
class.
fact, it was.
Thanks,
All
JD.
right. See you about 5.
All right.
Whatever time for you.
All right,
Yeah,
so now we're into
luck.
our RF safety. So RF safety, as we discussed, you can actually do some damage by by throwing RF fields at too big of a power level right at somebody. So there are a couple of different things to note. One is that it's non-ionizing radiation. If we think back to the electromagnetic spectrum, ionizing radiation has enough energy per photon that it can actually rip an electron away from an atom. This does not. Radio frequency energy is relatively low energy, at least as far as the body goes, and as far as on a molecular level. However, it does have enough energy to macroscopically heat things, as we discussed, like body tissues and things like that, by vibrating the molecules back and forth. So this is known as non-ionizing radiation, which means it doesn't have enough energy to damage DNA. That does not mean, however, that it can't cause harm. So there are limits which exist for people and being near antennas that are based on frequency, and it's measured in milliwatts per square centimeter, I believe. And because there are 3 different ways to calculate this, well, you can use FCC OET Bulletin 65. You can go get it and figure out how it works. You can use computer modeling to say, here's my station, and here's what all the fields should look like. Or you can actually walk around while you're transmitting and use a field strength meter and see how much RF is floating around. Now, that FCC Bulletin 65, this is actually a mathematical calculation of the implementation of FCC Bulletin 65. So let's say we're running 100 watts. We have a 6 dB antenna. We're 8 feet away from the antenna, and we're at 28 megahertz, which is the 10-meter band. And this basically says, okay, here's a controlled environment, which means you are in control of everybody that's walking through the area. Here's the uncontrolled environment. And notice that the limits, the maximum permissible exposure, are considerably less, approximately 20%, in an uncontrolled environment compared to a controlled environment. In other words, that's basically saying, okay, well, in order to meet that standard for the controlled environment, you can be within almost 9 feet of the antenna. And we said 26 feet. Okay, so that's safe. For the uncontrolled environment, which basically means, like you put it on the roof in a museum. Okay, well, if some people can somehow get that close to the feed point, this is how close they can be and still be safe if you don't have any idea who's walking through. So basically, it's the difference of putting a fence up around an antenna or just having people walking by. So let's say that you have something on your car and you're running 1,000 watts with, let's say, 5 dB from your car, and you're in a parking lot and people can get within 6 feet of the antenna on the roof of the car, and you're on 28 megahertz. Is that safe? Yes or no? No, it is not. Okay. And in fact, you would have to, if running that power level from your car, people walking by would have to be 55 feet away from your car to be safe when you're transmitting. So it's important, notice, that this says average power at the antenna. The question is, what's your average power? Well, what if you transmit for 5 seconds and then you don't transmit for the next 55 seconds. So that might drop your average power down, but usually we use worst case. The worst case is going to assume that you're transmitting full power all the time. That way you're guaranteed to be safe. So what this really means is there are two things you can do. You can put a big fence around your car. You can put up a rope that says danger, danger, danger. Or if you knock it down to 100 watts, well, we're getting closer. Okay. So let's go down to 50 watts. And okay, for a controlled environment, now we're okay. And let's say, okay, 25 watts. And nope, we're still not quite there. But now let's see if we can keep people to within about 8.5 feet of your car, then it's okay. At that point, you're basically saying, okay, well, the other thing we can do, let's put up a little caution tape, and now everybody's safe. So the other thing to do with this is once you do this calculation, if it's in a fixed location, like at a station, you'd basically run these calculations and then post it on the wall saying, look, I did it. Because everybody who's got a license, if you build a station, you're required to run the safety calculations. Similarly, if you change any equipment, for instance, or change antennas, you're supposed to run it again. The definition of duty cycle during averaging time for RF exposure is the percentage of time that a transmitter is transmitting. So if you're doing 100 watts, but you're only doing it 10% of the time, you're averaging 10 watts. Duty cycle and safe RF exposure levels. RF is affected by the average exposure to radiation. Again, 100 watts 10% of the time is only an average of 10 watts. So in theory, you could use that 10 watt value and say, I'm using, my average power at the antenna is only 10 watts. You could do that. Again, I like to do worst case because I don't really know how it's going to be used in the future. So I think about worst case. If you went from 100% to 50%, that allows you to use twice as much power. So if you run 100 watts for 100% of the time, that's the same as running 200 watts for 50% of the time. Why do exposure limits vary with frequency? And that is the fact that our bodies are typical average size human. So it's going to be different for kids or for very tall people. The exposure limits might be a little bit different, but by and large, the human body absorbs more energy at some frequencies than others. In other words, it looks, well, at very low frequencies that radio waves sort of like pass around or through without doing anything. At shorter wavelengths, it actually seems like it would, affect us more. The peak absorption of the average human occurs at 50 megahertz. And if we look at our chart, we know that's on the 6 meter band. So the lowest exposure limits occur on the 6 meter band. What factors affect the RF exposure of people near an amateur station antenna? Frequency and power level, distance from the antenna to a person, and the radiation pattern. So the radiation pattern, again, is very important. So what we're going to do is we're going to draw a dish antenna. Here's a dish, and we have our transmitter. And here's our dish, and our forward direction is this way. And we have 30 decibels of gain. And again, we're going to make it a 100 watt transmitter. Okay, so 30 dB, we remember from yesterday, every time we have 10 dB. What is 10 dB as far as power multiplication, everyone?
10x.
10 times. So we have 30 dB, which is 10 plus 10 plus 10, which is 10x and 10x and 10x, which is 1,000 times. So we have 100 watts times 1,000. So in this forward direction, we have 1,000 watts, 1,000 times 100, which is 100,000 watts. So when we run our safety calculations, what we need to do is go back here, and we're going to say we're running average power 100 watts. And what will we put in? This is in dBi. And we have 30 dB compared to a dipole, so you actually have to add 2, as it says. add 2.2 for antennas rated in dBd. So we're going to do 32.2 dB. And now we're just going to say, okay, we're going to be 50 meters away and on 432 megahertz, and go. And guess what? How far away? Even 160 feet is not safe for the general public. And why is that? Because with that much gain and that much power, we would have to be over 350 feet away to be safe for the general public. Because we have that much forward gain. We have a radiation pattern that is pointed that much in that direction. So that's where this comes into play. And that's why you have to take this class, because it's important to know this stuff. Because again, your license permits you to try all these things. Which of the following actions can reduce exposure to RF radiation? You can relocate antennas. You can put it up higher. If it's up higher, it's further away from people. And finally, you should regularly evaluate your station for safety. Whenever you make any changes to transmitters or antennas, you have to run the numbers again.
Question?
Yes.
When you're calculating that distance,
Mhm.
is that just distance over the ground, distance in the air, or a combination of the two?
It doesn't matter what the path is. It's basically the point, the distance between 2 points. So if the antenna is 100 feet in the air and everyone else is on the ground, they're going to be at least 100 feet away no matter what, even if they're directly underneath. So it's the
Well, no.
distance from the feed point. Whether that's vertical or horizontal doesn't really matter.
But if you're calculating where to put the fence and you need 170 feet of distance,
Then you would use
basically make a
trigonometry.
right angle.
Yep. So let's say you've
triangle
got
and-
an antenna that's 100 feet, right? And you need people to be at least
160 feet away.
160 feet. So then you'd have to you could actually basically say, okay, well, it's 100 feet up by trig. How far away do we have to be?
A
A squared plus B squared equals C squared.
equals C square.
Yep,
Okay. got it.
exactly.
Thank you.
Most of us are lucky enough to not have this problem because we don't run that much power and we don't have antennas that big, nor towers that big, sadly. All right, so we're up to page 77, which is station setup and operating controls. And is there anyone else who would like to take a 5-minute break to go use the bathroom and grab a new refresh of coffee?
Sure, yeah.
I would like to.
Yeah.
I will be
Like a
back in
plan.
5 minutes.
Yeah, I could do some coffee.
All right, everybody ready to go? Is the 5 minutes up?
I had looked over and my whole screen was turning colors and I realized, oh, yes, sharing screen.
Yes, indeed. And we were going to go back to that too. All right. Does anybody have any questions before we move on? And to answer your question about building a shack, yes, like, for instance, I have right now, I have 4 or 5 HF radios and a handful of other mobile radios and FM handhelds. We've got 4 hams in the family. We have 6 Yaesu FT60 handhelds and a handful of Baofangs that I use as loaners, a couple of DMR handhelds, because, why not? You can never have enough radios around. But yes, you really, actually, it said you can only use 1 radio at a time. That's actually not true. There's actually a contesting category that you can enter contests in, which is SO2R, which is single operator 2 radio. Although I've never been able to succeed at that. I don't know how people do it. All right, moving right along. We are now on page 77, which is station setup and operating controls. And this is where it really gets fun. So we're talking about power wiring. Why are short, heavy gauge wires used for a transceiver's DC power connections? And what we are going to do is talk about good old Ohm's law. Now, I will say also that in my experience, 90% of problems, both in radio and in the real world when you're working, if you do electronics, come down to Ohm's law. The reason is that here's a power supply and here's our transceiver, XCVR. So we have our red and our black that connect the radio to the power supply. When we are transmitting, let's say we are pulling a current of 10 amps. Okay, so what is the difference between this wire, and there's a matching black wire that goes along with it, and the other one, which I just showed you, which is straight? What is the difference between those 2 wires?
The one you just drew is now a longer path.
One is doing the same thing, but over a longer path. And resistance is equal to the resistivity of a wire times its length. Right? So the overall resistance is the resistivity of a given wire times its length. Now, if I had a wire that was this big compared to a wire that was this big, it's not only length, it's also the diameter. So the thinner wire is going to have a higher resistance than the fatter wire. So the rule of thumb is when you're making a connection between a power supply and a radio, you want your wires to be 2 things. What are they?
Fat and short.
Fat and short. That's right. You want fat, short wires because thin wire has higher resistance and E is equal to I times R. Is that true? Yes, it is. And power is equal to I times E. So the thinner your wire is, the more voltage drop you're going to have, because this is now a resistor, and it's a resistor going that way and a resistor going that way. There's going to be a voltage drop in the wire that's equal to I times R. And in fact, the voltage drop can get big enough that if you have, let's say, a 13.8 volt power supply, and if you have 1.5 volt drop here and 1.5 volt drop here, you only have 10.8 volts available at the radio. And guess what happens when you transmit? What do you think happens?
You'll be using more power, so get a drop.
Well, you're going to be pulling more current, and then all of a sudden you've only got 10.8 volts on the radio. What happens to your control circuits? Which normally take 12 volts to run.
Non-op.
It actually turns the radio off. Yeah, that actually happens. If you have too big of a voltage drop, we actually had this at work once. We had a camera system that whenever the lights came on, the camera shut off and they had to reboot. And that was because the lights drew a lot of current through this long, thin wire. And our normal voltage, which was 24 volts, dropped down to 16. And it wasn't enough to keep everything working. So this is a real world problem. And it happens all the time. And sometimes what happens can look really weird, but it usually comes down to good old Ohm's law. Okay. Let's see. Which of the following is an appropriate power supply rating for a typical 50-watt output transceiver? Okay, so we're going to do some basic calculations here and say that this load is 50 watts at 13.8 volts. 13.8 volts, by the way, is the nominal voltage for a car battery. They say it's 12 volts. A fully charged car battery is 13.8 volts DC because a single cell lead acid cell is 2.3 volts. So times 6 is 13.8. So if I hook this up to my car battery, here's our plus and here's our minus, or to our power supply, it doesn't really matter which one. To generate 50 watts of RF, you basically have efficiency issues in the transceiver. An amplifier will typically run between 50 to 60% efficiency. And on top of that, you typically have about 1 to 2 amps just to keep the lights on. So basically running the electronics, keeping the light lit, stuff like that. You know, the receiver, basically 1 or 2 amps. So if we look at that, how many watts, if we're running at 50% efficiency, does it take to make a 50-watt output? It takes 100 watts because about 50 watts of it disappears in heat. And actually, you'll see that a typical 50-watt transceiver will also have this thing on the back that looks like that, which are cooling fins, so that all that power that's dissipated as heat has somewhere to go without cooking the radio. So you have 100 watts coming in at 13.8 volts. That is about 8 amps, plus 1 or 2 amps to light everything up. Add those together, you get about 10 amps. And you leave a little bit of headroom. And so you say, okay, given those choices, either 4 amps or 12 amps, I go with the 12 amp power supply. That's a pretty common size. It allows for, you know, okay, we want to hook up a small light. We want to hook up a charger, something like that. A 12 amp power supply is suitable for a 50-watt radio. Okay, what signals are used in a computer radio interface for digital mode operations? Okay, so one of the things that we do is we hook up computers to everything now. And so here's a digital radio interface. Here's a computer. And here's the radio. Okay, so we basically need something to act as an interface between the two. So our computer is going to have audio, and the radio is going to have audio, and it's going this way. And then the radio is going to produce audio, and that's going to have to somehow get to the computer. So this thing could be something as simple as a sound card, which can be inboard or external to one of them. And effectively, this is the computer speaker. And if that's the sound coming out of the computer, what input would that connect to on the radio? That would be the microphone. Conversely, we have a speaker on the radio, and that audio would connect to the computer, has a microphone input. The sound card basically connects as an intermediary. So basically, we have our audio going back and forth, where the computer basically sends audio to the radio and back and vice versa. And then we also have this additional line, which goes out and through and out to here. And this comes from the computer to the radio and is the PTT, which is the push to talk line. That's basically necessary to key the radio, to switch it from receive to transmit. On a handheld radio, that's your push button. On a microphone, that's your push button. You push to talk, and it's known as PTT for that reason. Okay, how are the transceiver audio input and output connected in a station connected to operate using FT8? It's the exact same way. Basically, if you're using a computer running software, you just have to connect the radio's input and output audio to the computer's input and output audio so that the software has something to work with. Which of the following is made between a computer and transceiver to use computer software when operating digital modes? Well, your choices are basically you connect one to the other. So line in, which is known as the microphone, connects to the speaker output on the radio. Okay, so now let's say that we have these wires here and we have the radio connected to this antenna, which is up here. And the antenna is generating RF energy after modulating the signal, and you are not using shielded wire, and some of your signal is getting down to here. You have a push to talk line, which is a voltage. You have audio, which is a voltage. So what happens if some of your RF transmitted signal gets picked up because what is any piece of wire? What can any piece of wire act as, everybody?
An antenna.
An antenna. So if we have any piece of wire here, we have these wires connecting radio to a sound card and a sound card to a computer. If any of those pieces of wire acts as an antenna, which they invariably will, all of a sudden you can get additional signals that are getting into your sound card or getting into your computer or getting into your radio that you didn't plan for. So that can distort your audio. It can cause your radio to lock up and transmit. How does everyone think I know this?
I'm assuming personal experience.
That's right. Personal experience. I've had it happen. The other thing it can do, which is really fun, is that it locks up your computer and you have to reboot your computer. That's the best. So how do you avoid all of these problems? Well, what we're going to do is have our piece of wire, and we are going to say that any piece of wire that is carrying a current, let's say there's a current induced on it from an RF field because it acts as an antenna, it's now going to have a current flowing on it. Well, what does a current make as it flows?
Magnetic field.
Magnetic field. Okay, so as it does, we have a magnetic field going this way around the wire. Okay, so there's not a lot we can do about that, but what we can do is say we're going to put something on here that reacts to magnetic fields. And this is something that is in the shape of a donut that looks like this. And this is known as a ferrite. And it's either a ferrite choke or a bead or a core. It's basically a ferrite. Okay, so a ferrite is usually made of iron or nickel powder plus glue baked into a donut. Now, does anybody have one of these nearby if they're on a computer? I'll bet you do. If you have one, hold it up in the air. Anybody?
I have
I
several,
have-
but they're out in the garage.
I've
Me
got one
too.
right
I have
here.
Plenty, but not with me here.
I've got one right here.
One across the table that won't reach over.
Yeah. So you notice right on your power supply going into your computer, you've got one of these, right? The reason that it's there is that if there is any RF energy that is floating down the line, what'll happen is that the magnetic field that's made will encounter this material, which is specifically designed because of the mix that it uses, like a certain percentage iron or nickel or other ferromagnetic materials, so that it makes a really good but lossy path for magnetic field energy. And they basically go there to die. So if the energy gets dissipated, what happens to the current that was making it? What do you think? If the energy, if the magnetic field energy gets dissipated, what do you think happens to the current, the current that was generating it? All that power disappears. It disappears as heat in the ferrite. So there is essentially very little that comes through to the other side, which is the same stuff that would cause your computer to stop working. And again, this is known as a ferrite choke. So what we do is we take our cables and we wrap them with ferrite, and we wind them through ferrite chokes. You can either snap it around it, or like you can take a ferrite choke that looks like this. If you have one that's big enough, you can do this with your cable. Go around and around and around and back out. The more times you wrap around it, the more effective it is. Now, interestingly, most ferrite chokes you will find are clip-on style, where eventually they make a donut, but they come in like a split half. And that's so you can take it on an existing cable and not wrap it around it. You can just basically split it at this point and then snap it in place. That actually works just fine. Now, on one of my cables, I actually have 5 ferrites to keep my computer from rebooting. 5 ferrites on a USB cable. Any idea why I have 5 ferrites? What's the most logical explanation? What?
Better to be safe than sorry.
Actually, I found that 4 ferrites was not enough. That I had a big enough problem that I tried 1, I tried 2, I tried 3, I tried 4. They didn't work. When I added the 5th one, the problem went away. So a lot of this is down to picking the right core, picking the right mix of material, and then figuring out how many of them you need to make it work. Which of the following conductors is preferred for bonding at RF? Okay, so we discussed something called safety ground, right? This is safety ground. This is basically your stake driven into the ground. So the question that I will now ask is, your house wiring at 120 volts, what is its frequency? Everyone?
60 hertz.
60 hertz. Think of this as RF. How many megahertz would that be? That'd be 0.000060 megahertz. We plug that into our formula, 300 F lambda, we get that the wavelength is about 5,000 kilometers. So what is 5,000 kilometers in practical terms? The distance from Seattle to New York, roughly. In other words, any piece of wire that you have isn't going to be a very good antenna at 60 hertz. So, you know, if you have, let's say, 100 feet between your radio and the ground, basically ground is ground. If you're at 0 volts here, you're going to be at 0 volts here, even if you have RF energy at 60 hertz. But now we're going to bring up a slightly different concept, which is the fact that we now have, we're going to call this ground, and we're now going to have 100 feet of wire connecting to your radio. But now we're going to take a frequency of 30 megahertz. And the only thing that we know is that ground is at 0 volts. So now we're going to use that same formula, 300 F lambda, and we know our frequency is 30 megahertz. So our wavelength is 10 meters, which is 33 feet. How long is our cable getting to our radio, everyone? Our ground cable?
100 feet.
100 feet. Okay. Well, 100 feet. Well, a wavelength is 33 feet long. And the only thing we know is that ground is ground. So we have this and this and this, and we can actually draw waves on this cable. So if this changes to 110 feet, are we at ground anymore? If it's 90 feet, are we at ground? Are we at 0 volts?
Ground is ground, right?
Ground is ground, but how about right here where you expect there to be ground on the radio? You have the cable, you have it grounded.
But doesn't that ground only zero out if your wavelength is zeroing out when it hits?
That's right. So
the
let's
wire,
say
but
that this cable is some random length, and it turns out that by the time you get there, your cable goes like this, and your wavelength goes like this, or you're on a different frequency. Is that at ground right now? Is that at 0 volts?
No.
Nope. So guess what? You are not at RF ground. Now, if I were to draw safety ground, because it's at 120 volts and 60 hertz, you're at ground. So RF ground and safety ground are two different things. And that's why safety ground, you can wire your whole house. It can be pretty much anywhere. That's no problem. RF ground, if you want to actually ground your equipment, depending on the frequency you're on, you want this cable to be like as short and straight as you can. Because as soon as you start being able to draw waves on that, you are not at ground anymore. So that's a very important distinction. The other thing with grounding is that RF, okay, let's say that I look at DC current, right? Here's the cross section of a wire. As current flows, it takes up the entire cross section of the wire. So whatever the cross section is, if I do something like this, it's going to fill up that whole cross section. So I get a big improvement by doubling the size, right? There's a lot more cross section. However, if I do RF, so here's my bigger conductor and here's my smaller conductor. RF has a really nasty habit. The higher the frequency you go, the closer to the surface the current likes to travel. At RF frequency, it can be almost assumed that virtually all of the current actually flows on the outside of the conductor, not on the inside. And this is known as the skin effect. So you basically have virtually no current flowing on the inside. So really only the surface of the conductor plays a part in figuring out what your surface area of what the actual current distribution is. So if I were to take that same amount of cable or same amount of copper and I were to pound it flat so that it looks like this, which one provides more surface area? The round one or the flat piece?
Flat piece.
The flat piece. And that is why if you're doing grounding, you want to provide as good a path for RF to pass. You use a flat strap. You use a flat piece of copper for grounding, for RF grounding. Provides the lowest resistance to RF current flow. Where should the negative power return of a mobile transceiver be connected in a vehicle? That's at the 12-volt battery ground, right? Not at any spot on the frame of the car. Now, it is true that for most intents and purposes, the frame of the car, everything's welded together and ground is ground. However, it is not designed the frame of your car, for instance, to carry 30 amps. You don't know when you try to put 30 amps through it exactly what's going to happen. The easiest way to get that 30 amps back to the battery is to go directly to the battery, right to the terminal. And that's going to basically mean that whatever your battery connection looks like, you're going to take the connector off and you're going to put another piece of wire right there in line with it in parallel. You're basically going to have your car circuits, and then you're going to have your radio circuits coming directly off the battery. The other thing is that, does anyone have, it used to be called a cigarette lighter adapter. Now it's an auxiliary power adapter. Those are typically not rated for more than about 5 amps. Some may say a little bit more. If they're even rated 10 amps, you're not going to hook a 100-watt radio to it. It's not designed to handle that much power. How do you determine the length of time that equipment can be calculated from a run from a battery? You again have something called a watt-hour rating or a volt or an amp-hour rating. A watt is basically volts times amps, which is power, times time. So a battery might have a rating of 2000 watt hours at 12 volts. Well, divide that. You end up with, let's see, that would be about 180 ampere hours. You could also have something that is simply rated at 180 ampere hours. I typically like ampere hours better, but they're really the same thing. If I have a 100-watt radio, ideally I can run this for 20 hours because 20 hours times 100 watts is 2000 watt hours. Similarly, I know that if I'm drawing, let's say 10 amps, I can run this for 18 hours. I get about the same answer. So you basically have a capacity of your battery that's defined in something hours, and you just basically can divide it by the load and figure out how many hours it's good for. Okay, operating controls. We're on page 80. Single sideband. Okay, so this is why I actually pulled up the web SDR. And I'm going to unmute this and hopefully make sure that I share it with audio like that and turn off the mute and hopefully everyone can hear it. Everybody hear that?
Yep.
Okay, so we're going to go over to single sideband. Hopefully I can find one. There's one. Okay, this is single sideband. We are now listening to the upper sideband. The bar in the center of this right there is the tuned frequency. Here's another one. Notice what happens if we, because we don't have a reference point for the carrier, if we mistune it. So it's very important to learn how to tune properly to make it sound normal. The other thing we can do is if we listen on the wrong sideband, we get speech inversion, and it sounds completely wrong. So that's if it sounds right. Now, if we were to take this signal and overdrive it, what we would find is that it takes up too much space and sounds distorted. So if we put too much gain, let's say we yell into the microphone or we have too much audio, it just basically clips and gets distorted. What's the result of tuning an FM receiver above or below a signal's frequency? You get the same thing. Basically, if it's not lined up on frequency, it doesn't sound right. Okay, which of the following can be used to enter a transceiver's operating frequency? Basically, this is what we're going to do right now. This is the equivalent of spinning the tuning knob. So we're just changing the frequency that we're running on. Everybody can see the frequency at lower left, 178, 179, 180. So that's the right frequency. That's how we alter the frequency. We have a keypad or a VHF knob. To access a favorite frequency, you could actually store this in memory. Say, okay, we like this particular frequency because we meet on this frequency, so we can store it in memory. The scanning function of a receiver is to basically have a whole bunch of things programmed in memory and scan a range of either frequencies or a range of memories that you are particularly fond of. I have in my handheld, I have programmed in about 30 different repeaters and different simplex frequencies that I use, and I just set it to scan all the time. The purpose of a squelch function. Okay, I think this thing does squelch. So here we go. We're going to tune to an empty frequency, and we're going to turn the squelch on. What happened to the signal, everyone?
Got muted.
Got muted because there's nothing to listen to. So basically, squelch quiets the receiver when there's nothing to hear. Now, here's a question. Does everybody hear that background noise? Not that. Does everyone hear that background noise that we call static?
Yeah.
Yeah.
What is that?
That's
What is that actually?
cosmic radiation.
That's
background.
basically the sound of everything. That's not specifically on that frequency. So it's all the cosmic background radiation and radiation coming from on that frequency. Because remember, we're looking at a color of light or energy on a particular frequency. And we're actually listening to it. So we're basically opening our eyes and looking up at everything using our antenna as our eyes and the radio as an amplifier and saying, what are we hearing? So that is the sum of everything that we can hear, that we can see on that frequency. So basically, that's the sound of stuff coming in from space. It's the sound of all the weak signals that are on that frequency that are bouncing around Earth. It's the sound of distant stations that we can really not hear very well, but they might be there. It's the sound of noise being generated on that frequency by power supplies, by the guy's TV 10 miles away that's making a little bit of noise on that frequency. So when you tune to something like this, and you hear static, some of it is static crashes from thunderstorms that might be 1,000 miles away. Some of them could be static crashes from thunderstorms that are 5,000 miles away. You don't really know which way it came from, but that's the sound of everything, which I think is kind of cool. How is squelch adjusted so that a weak signal can be heard? You basically take the squelch and you do this with it. You turn it off. You open the squelch. So this would be the squelch going up to a high point. And if I turn the squelch off or open up the squelch, as it's called, I'll hear all the static. So if I'm listening for a weak station, I actually want to hear all the static. Let's say that I'm over here. Notice the squelch is still on. It keeps going on and off, and that's because there's a station that's loud enough to go away and then come back. Okay. Repeater offset. Okay, what is repeater offset? Repeater offset is something that you are all going to experience at some point. So a repeater is a kind of a unique beast that it has a receiver and a transmitter in one place. And they are connected by this thing called a controller. And they are connected like that. The controller determines what's going to happen and when. So they are either connected to separate antennas, or even trickier, they could be connected to the same antenna. If they are connected to the same antenna, there is a splitter right here called a duplexer that allows, because if you think about it, what use is a repeater that it hears something and then 5 seconds later it transmits it? Ideally, when something is coming into the receiver, it's going to go through the controller, out the transmitter, and back out to the world on a different frequency. That is the whole point of a repeater, to repeat in real time what it's hearing. Well, if it's using the same antenna, that actually works by basically using the antenna twice on different frequencies. The way that we do that is that this duplexer is actually a really, really, really narrow filter that separates signals coming in on one frequency and sends them to the receiver and allows frequencies going out on a slightly different frequency to not interfere with the incoming signals and vice versa, which is really an amazing thing. A receiver duplexer, the separation between the two channels is typically 110 dB, which is 0.00000000001 times. So that much of the signal going out gets back in. Not very much, right? Any more than that, and it could actually be enough to interfere with it. So the way that this works then is that the receiver listens for people calling on one frequency and retransmits signals to everyone else on a different frequency. This difference in frequency is known as the offset. And on the 2-meter band, the typical offset is 0.6 megahertz. On the 70 centimeter band, the offset is typically 5.0 megahertz. These are very important to note. So that's basically how a repeater works. So if we say that a repeater's published frequency is 146.72 megahertz, what you would have to do is when you transmit, your radio would switch to 146.12 megahertz, because that is the frequency that the repeater is listening on. So you would transmit 600 kilohertz or 0.6 megahertz lower than the repeater's output frequency. The nice thing about that is that everyone else who's listening on 146.72, which is the published frequency of the repeater, hears you going through it. Now, that band goes from 2-meter band goes from 144 to 148. At 147, there's a dividing point. So below 147, we have a negative offset. Above 147, we have a positive offset. So if my published frequency is 147.14, the shift would be a positive offset. So you would transmit on 147.74. Below that, let's say that my frequency is 145.13. Your transmit frequency would be 144.53, 600 kilohertz lower. And that's how offsets work. Once you program your handheld radio to do that, it will automatically change the frequency when you hit the push to talk button. Okay. What function is performed with a transceiver and a digital mode hotspot? That would be communication using digital voice or data systems via the internet. So if we're using a digital handheld radio, that is digital audio. If anyone's familiar with actually how we're talking right now, we're basically doing a form of voice over internet protocol, which is exactly what happens over over the phone. It's only transmitted to analog audio when you need to hear it. As soon as you talk into your phone, it is transmitted into digital signals, which is why sometimes it sounds so weird if the decoding is messed up or the encoding is messed up. It's converted to digital signals and they're assembled back into something you can listen to. If you're using a digital radio, it actually does the job for you. It converts your voice into a digital bit stream and then translates that to and then sends that along over the airwaves. Now, again, you can actually hook up a hotspot and connect your radio to the hotspot and connect it directly to the internet. On the other end, there might be another hotspot where somebody has a digital radio, and you're basically digital all the way going from radio to the internet back to a radio. So you can use a radio like a radio and actually use the internet as a bridge.
Basically going from radio waves to digital translates from digital to radio.
Yep. And actually, our repeater here in Eugene is tied into something called Echolink, which is an internet gateway, which allows you to use a cell phone or a computer, which is running the software to do it. And that actually is directly tied to the internet over Wi-Fi and allows you on the other end to pop up on an analog repeater as if you were a user on the repeater locally. There's a lot of cool merging of technologies. A lot of people have come up with, for instance, Raspberry Pi or Arduino based systems, which makes these things incredibly compact. You know, really, really compact gateways. A talk group on a digital repeater, that's basically if I'm operating in group 1 or group 2, I would pick the group, I would give it a number, and that would allow all the people using that talk group to talk to each other without hearing everybody else. So it's kind of like a private group. Now, it's important to note that nothing on the radio is private. We are not allowed to, with a very few exceptions, we are not allowed to encrypt anything or obscure a meaning. So that means, like, you know, we're not really technically allowed to pass coded messages saying, hey, you know, football 26 might mean I'll meet you at the zoo. We're not allowed to do that. You're not allowed. That's not encoding per se. It's not encryption per se, but it's obscuring something's meaning. If you want to have a perfectly private conversation with somebody, you call them on the phone. That's what that's for. The radio is used for, you know, things that are designed to be open and accessible to the public. So if you're expecting there to be something that's really got to be private, you should go grab a phone line. Now, what's useful about this, however, is the fact that we can actually have group conversations. You know, this ham radio is the world's oldest party line. So we have a Sunday night chat where we all get on the 10-meter band, 28.450 in Eugene, and we get 10 or 12 people, and we have an old-fashioned, non-controlled roundtable where we just talk about anything and everything. And it's just a good chance to sort of, like, you know, let ideas germinate and talk about how your weekend was and things like that. That's just basically a get together on the air, sort of like you'd have dinner at a restaurant, except that we're doing it over the radio. Okay, a DMR code plug. It's a complicated term for essentially a set of repeaters that you program, or a set of different addresses that you program into a radio. So access information for repeaters and talk groups. That's a code. That's called a code plug. I don't know who came up with the term. I don't like the term, but that's what we have. How is a specific group of stations selected on a digital voice transceiver? You enter the group's ID code, and that basically connects you to that group. One of the bits that you enter in the code plug is called a color code. What's the purpose of a color code on a DMR system? A color code establishes groups of users. So it's a part of the code plug. And it's called a color code. Which of the following must be programmed into a D-Star digital transceiver before transmitting? It's a good idea even on DMR systems. You basically, because it's digital, you put your call sign into the radio because it sends out digital packets. So it basically identifies the packets with your call sign, so people know who you are. The advantage of having multiple receive bandwidth choices. Okay, so we're now on page 83. And this was the main reason that I brought this up as well. So we're now talking about this right here. Okay, so we're going to unmute it and turn off the squawks. Okay, so we said that a single sideband signal is about 3 kilohertz wide. We can basically mess with the filter bandwidth by doing this. So notice our filter is now 500 hertz. How well does everybody hear that audio? Everyone?
Not that well.
Can everybody make it out? I can't.
Yes. I can't either.
Yeah, it's just basically there's audio there, but it sounds like, you know, it doesn't really sound like a person. Here's another one.
Sounds like Darth Vader breathing.
Yeah, so this is not an appropriate filter bandwidth for single sideband. But 2.4 kilohertz is a pretty good narrow filter for single sideband. So that's why for single sideband, we go 2400 hertz, 2.4 kilohertz. Now, what we're going to do is we're going to slide over to the Morse code part of the band. And we're going to go to a busy part of the band. What do you hear? How many different signals do you hear in there?
Quite a few.
Quite a few. Well, if we're listening for one, why do we need to listen to all of them? Unless you're trying to pick one out. Let's say you've got one picked out. We don't need that much filter bandwidth. So what we're going to do is we're going to hone in on one in particular. And 500 hertz or 0.5 kilohertz is a good starting point. And notice what it does. It basically blocks out all the extraneous noise around it. We could always widen it out where we pick everything up. But the nice thing about narrowing it down is that it keeps everybody else down. So 500 hertz is a good filter for Morse code. Same thing is true with digital. So let's see if I can find a nice digital signal to zero in on. That should be one maybe. There's a digital signal. Right? Fairly narrow. You can see actually how much space it takes up. It's pretty narrow. Notice Morse code is really narrow. There we go. There's one. So you can see pictorially how much space each of these signals takes up. There's another digital one. We could actually filter down even more.
Hey, Scott, could you tell us what some of this Morse code is saying?
Yeah, sure. Oh, he's Maritime Mobile /MM. K0MNE /Maritime Mobile. Which means he's on a boat. He's on a boat in international waters as Maritime Mobile. Yeah, every time I go there. EA5KO, he's in Spain. K3WW, I know he's in Pennsylvania because I know who it is.
Awesome.
So let's do this one. And notice that this one's running a little bit slower. Name is Fulvio. And then he's going to repeat it. His name is Fulvio. He's EG5NDO. He's in Spain. Or she. I don't know which.
Scott, in Morse code, is this in English only, or they can also do it in their native language?
There's virtually every language that has a translation. Like I've heard Swedish Morse code, which uses the standard letters that we know, plus a few others. If you think about Swedish with like the A with a little circle, A with the umlaut, O with the umlaut, U with the umlaut, those are all different characters. So I've heard Swedish Morse code. And all the words are in Swedish. So, you know, I've had contacts in Spanish over Morse code. You know, I don't know if there's an N7JI. There probably is, but I don't think that most people would actually bother sending it. I don't know if there's a, you know, the Y, LL. I don't know that that's specifically a different character or not. But I've had, you know, I mean, basically it's the international Morse code. It's not American Morse code. So it's used for basically any language anywhere. And what you'll find is that most people like in Japan, they use Morse code. They use English characters. So they have a name that they spell in English, Masa or Taku, in English characters. And that's understood everywhere. Or for instance, there's something called an RST, which is a signal report. Now, I'm sure RST does not translate to anything in Japanese, but it is a signal report, so they know signal report, whatever that translates to in Japanese, is represented by the letters RST. Da-da-da-da-da-da. That's the same everywhere. So, it's kind of like it takes away all of the accents. It makes it a lot easier to understand each other. Okay, there's also something called receiver incremental tuning. So when I listen back into one of these, receiver incremental tuning, let's say I don't like the tone. So I tune slightly to make it more pleasurable to myself. Most radios will vary the transmit and receive frequency at the same time. Well, if you do that and the other person is locked onto your frequency, you will be moving at the same time. And they will have to retune because then all of a sudden you will be unpleasurable to them. So there's something called receiver incremental tuning or a clarifier, which allows you to decouple the two signals, the transmit and receive frequency, and shift one without shifting the other. Okay, push to talk. Push to talk
This
is
is the technique. Sorry, Scott. This is the technique we use when communicating with a satellite that is moving Doppler shift. The Doppler.
Yes. So very important. We're going to actually get to Doppler. So let's say that if we're looking at a satellite coming overhead, going like this, as the satellite passes overhead, as it's approaching you, its wavelengths are becoming compressed. As it's moving away, its wavelengths its waves are getting stretched out. Now, kind of like a fire truck coming toward you and then going away, like that. A satellite moving at 17,000 miles an hour is actually moving fast enough that it compresses the waves to a noticeable degree. So, for instance, if we're talking to the International Space Station on 437.800 megahertz, as it's coming, you actually would listen on 437.810. And as it's going away, you'd listen on 437.790. And you'd be able to tune your radio to listen on those different frequencies. While since you're transmitting on 145.99, as it's coming closer, you would actually do it on .985 because that will actually be raised, and going away 145.995. So these are actually a different amount of offset. So you would have to be able to independently adjust those as you go.
Does the radio do that automatically, or do you
Typically, no. That's something that you have to get used to doing. Some will, but most don't. Okay, so we're on 84. A transceiver is a device that combines a receiver and a transmitter. A transverter is a different device altogether. So what we're going to do is we're going to draw an electronic device called a mixer. A mixer looks like that. It takes a frequency 1 and it takes a frequency 2 and it combines them and generates frequency 1 plus frequency 2, frequency 1 minus frequency 2, frequency 2 minus frequency 1, and all kinds of combinations. It doubles it, it triples each one, it subtracts everything. So if we were to draw this on a map where we have 0 frequency up to infinity, and we have frequency 1 and frequency 2, the outputs that we get from this thing will be the addition, and it'll be the subtraction, and this one, and then 2 times 1 and 2 times the other, and 2 times 1 minus the other one, and 2 times 1 plus the other one, and then 3 times 1, and then 3 times. Notice what we get out. It's a mess, right? Well, if the one that we want is this particular one, what would we use to separate that from all the others? Everybody, what's that called?
Filter.
That would be called a filter. And what do we use to make a filter? We use two different components that are frequency specific. Frequency sensitive. What are they called? They're basic electrical components.
Capacitor and inductor.
Is it the transducer and the capacitor?
It's a
The
capacitor
inducer.
and an inductor.
Inductor.
So
inductor,
we would
that's it.
basically use our capacitor and our inductor. And we would basically do this. That would be a high pass filter. And then we would take that in series with something like this. And that would be a low pass filter. And we would pick these components so that our overall box looks like that. And we filter out just the ones that we want. So this right here, this device where you have a mixer and then a filter, this is known as a transverter or a mixer. Basically, what it does is it combines two different frequencies and generates another one that you can use. It basically is a converter that works in both directions as well. If you run it backwards, you can basically mix it with this one and get the original one. So it allows signals on one band to appear on a different band. That's known as a transverter, like a converter, a transmitter converter. What device increases the transmitted output power from a transceiver? To make a bigger copy of something, you use an amplifier. That would be, because it's RF power, you would use an RF power amplifier. Okay, so now, with regard to amplifiers, if we have a function, again, of in and out, ideally, we're going to have a linear relationship between input and output, where let's say we have, 0 to 10 watts in, that makes 0 to 1,000 watts out. Ideally, this is going to be a linear function, right? But what did we say? If we were to look at a transistor, it actually looks like this. It has this linear range. So do vacuum tubes. So what we have to do is basically shift our starting point over to here and shift our starting point on this side up to here. And this becomes our kind of like our 0 and 0. And we're allowed to go negative and positive. And essentially we now have this becomes a linear amplifier. This operating in this range where the response is basically flat allows us to operate and make a nice clean signal. This is typically used for single sideband because we are looking for an exact replica of what we put in. Now, the other trick though is, let's say that we are doing FM, and FM, what do we vary with frequency modulation, everyone? And we remember this?
Frequency.
We vary our frequency. Okay, so does that matter at all? Does it depend at all on amplitude? Yes or no?
No.
It does not. So does it matter if we make an exact copy? Not really. It just matters that the frequency is maintained. So if it's, let's say that we make that copy and it's like smaller, and then it gets bigger and smaller and bigger and smaller, the frequency is still there. Just that the amplitude is bouncing all over the place. So what happens if we take it and we clip it like this so that we flatten everything out and we just have a bunch of frequencies in there? This is actually what an FM receiver does anyway. It clips anything above or below a certain amplitude and levels it all out. And then it basically just has the frequency on the inside, which is essentially exactly what you started with. So in this case, we don't need the amplifier to be linear. And in fact, that actually comes into play because we have a switch on our FM amplifier or on our VHF amplifier, which selects either sideband or FM, because it biases the transistor in a different place based on what's needed. So typically a sideband amplifier needs to be cleaner than an FM amplifier, which also means that it's not as efficient. Okay, so for sensitivity and selectivity. Okay, this is going to involve everybody yelling something out. Okay, okay, let's see, I need a volunteer who can whisper really quietly. Anyone? Don't be shy. Okay, who was whispering? Was that Travis? Okay, so can anyone make that out? Go ahead and say something. Okay, the ability to hear something that's really quiet is known as your sensitivity, right? A receiver that has good sensitivity could actually amplify that really weak signal very well. That's sensitivity. All right, ready? Now on the count of 3, I want everybody to unmute if you can and shout out a number. All right, ready? Everybody unmuted who wants to do it? Okay, on the count of 3, shout out a number. 1, 2, 3.
7.
7.
Okay, well, basically, if I were able to pick out one of those, I thought I heard someone say 7, maybe a couple people said 7. That's selectivity, the ability to selectively hear. So receivers have selectivity that's based on mode. Also, your ears are somewhat selective if you can listen to one particular pitch of signal over another one. So that's known as your selectivity. An RF preamplifier, if you're listening to signals coming in, this is actually really cool. Okay, so now we're starting to get into the system design of an RF system. So we have an antenna, and let's say we have a signal coming in that by the time it gets there, it's minus 130 dBm. Okay, minus 130 dBm. That's just a certain level compared to a milliwatt. So this is actually 0.00000000001 watts. That is the amount of power that is coming down the antenna, right? Everybody good with that number? Now you see why we use negative 130 dBm, because this number doesn't make a whole lot of sense. That's a lot easier to deal with. Okay, so now we have this cable, which comes down to here, and we have a receiver that has a sensitivity of minus 135 dBm. And in our cable, we have a loss of minus 10 dB. So by the time it gets there, how much signal will actually reach the receiver? Minus 130 minus 10 is minus 140 dBm. How does that compare with the receiver's sensitivity?
It's too low.
Too low. So will we hear anything?
No.
There's nothing to hear. Okay, so now what we're going to do is right in front of the receiver, we're going to put a little box, which has a sensitivity of minus 135 dBm. And we're going to say this has a gain of plus 10 dB. All right. Okay. So right here, what is the signal that's coming down the pipe? Minus 130 minus 10 is minus 140. Will that receiver preamplifier be able to hear anything? It has a sensitivity of minus 135. So it's still no good. Now, what we can do with this is we can take that preamplifier and we're going to take it and stick it all the way up by the antenna. It still has a sensitivity of minus 135. Okay, so what is the signal coming into this thing? It's minus 130. So just by moving it, we have made it so that it couldn't hear, but now it can. Now there's actually a signal that's worth amplifying, and it has a gain of plus 10 dB. So now our signal is, at this point, it's minus 125 dBm. And then we subtract our minus 10. And now we're at minus 135. Oh, sorry. we're at minus 120. And now we're at minus 130 dBm again. And how about our receiver? Can we hear the signal? The answer is now yes. So by taking our receive preamplifier and putting it close to the signal that we're trying to receive, this is exactly what happens with cable TV. If somebody comes out to your house and says your signal coming down the antenna, coming down the cable to your TV is too weak, they will put a preamplifier way upstream so that the signal is boosted, so that by the time you incur the losses, it has a big enough signal to actually overcome the losses, that you can actually still hear something. And this is basically system design at this point. This is how you decide where to put an amplifier and how big to make it. If it turned out that you had lossier cable, maybe you pick an amplifier that has a gain of 15 dB. It's a slightly different amplifier. It has one more transistor. And then your signal is minus 125. So if your receiver had a sensitivity of minus 125, then that would actually be something that was necessary to do. So again, this is actually where we start getting into system design, right? Like from a system viewpoint. So you want your preamplifier as close to the antenna as possible, because you can't amplify what you can't hear. A mixer converts one frequency to another. An oscillator is a tuned circuit that generates a signal at a specific frequency. When we start using a mixer, if we combine something coming in off of an antenna, we mix that with another frequency to generate a third frequency. That additional frequency is typically made inside the piece of equipment, and we use an oscillator to do that. That can be a crystal, that can be a capacitor and an inductor with feedback and a transistor. And because it has a capacitor and an inductor, it's tuned. If they're variable, it becomes tunable, in which case you can actually change the frequency. The act of combining speech with an RF carrier signal, we're on page 86. That's called modulation. Okay, radio frequency interference. We're on 87 now. What can cause radio frequency interference? Fundamental overload, which basically means something is just too loud. In other words, it's not trying to overload you, but your receiver has no ability to reject that signal. There's just too much there. Harmonics. A harmonic is, let's say you're operating on 10 megahertz. A harmonic would be an integer multiple of that, kind of like in music. You know, an A is 440 hertz. The lower A below that is 220. The next one above that is 880. So it's an integer multiple. So that would be a harmonic, which would be of 10 megahertz. The next one would be at 20. A harmonic generated by a transmitter could cause interference. A spurious emission is a signal that's generated that is not harmonically related. So a transmitter operating at 10 megahertz might suddenly start putting out, if it's not built correctly, an output at 17 megahertz, which has nothing to do with the 10 megahertz at all. What's likely happening is that there is some kind of capacitance and inductance in the circuit that's actually causing it to oscillate at a frequency you didn't expect. And there's that capacitor and inductor again, forming a tuned circuit. If your station is functioning properly and it doesn't cause interference to your own radio or TV, that is a good indication that if your neighbor's TV is getting affected, that there's something wrong with their TV. So the question is, if that's happening, are you responsible for fixing it? So if you have a ham license and you are operating legally, you are operating under something called Part 97 of the FCC rules. Basically, that is the rules that govern amateur radio operation. We are a licensed service. Now, there is also an unlicensed service, which is known as Part 15. Part 15 is unintentional radiators, or radiators that are of a sufficiently low level that they are not regulated. Like a computer power supply is a Part 15 device. A a cell phone, I believe, is actually a Part 15 device, depending on the frequency that it's operating on. You know, a mouse, a wireless mouse, that's a Part 15 device. If you are transmitting and your neighbor's wireless mouse stops working, that is not your fault. You are a licensed service. Part 15 device is an unlicensed device. Therefore, you are not responsible for the interference that you cause to them. You might want to help them, in which case you might want to come up with some method by which you don't interfere with them. Or maybe if it's a wired mouse, you teach them all about, you know, interference reduction. You basically like take their cable and wrap it around an RF choke, and maybe that reduces the interference. So we have the opportunity to work with them, but you're not required to. If you have a non-fiber optic cable, so classic old school cable TV, and it's being interfered with when you transmit, make sure all the cable connectors are tight. Loose connectors will let signals leak out of the cable system, and if something can leak out, RF can also leak in. A broadcast AM or FM radio like the one in your car, those actually will receive ham radio's frequencies. Well, not on purpose, but basically if you're transmitting with enough power and you're near an FM radio, it might actually receive you because it just can't handle that amount of RF nearby. My parents, when I used to transmit as a kid, would always hear me on the stereo. Even if the stereo was turned off, they would still hear me on the stereo. Fundamental overload of a non-amateur radio or TV receiver can be reduced or eliminated by putting a filter on it. It used to be that when we used to have wired telephones that would be plugged into the wall and we rented them from the phone company, if you told them that they were being interfered with by a ham radio transceiver, the phone company would actually come out and install a filter on your phone to keep it from getting interfered with. Which of the following can reduce overload of a VHF transceiver by a nearby FM commercial FM station? So if interference works one way, it can work the other way as well. I remember that I used to live near a station in Maryland called WJOK, all comedy all the time. It operated on 1100. And I used to, no matter where I was tuned, whenever I was driving by their station transmitter, I would receive them on any frequency. And that's simply because my radio was not good enough to block their signals. So how do you do that? How do you deal with that? Let's say that they are right next door to you. You install something called a band reject filter, which basically is a flat open pass band, except for one little notch taken out of it. So now is a good time to draw. No, I didn't want to do that. Shoot. How do I get back to it? Sorry, give me 1 second here. There's my Zoom. Okay, I'm going to share and pick the whiteboard. There we go. Okay, so here's my frequency chart. I'm going to draw a nice flat line from 0 to infinity. So if I look at something called a filter passband, I can have something that's flat up into this point. The high frequencies get through. This is known as a high pass filter. If I have one that allows low frequencies to get through up to a point, that is called a low pass filter. If I somehow manage to intersect these and pick that range, then the overall signal looks like this. Only a certain band of frequencies get through. That's called a band pass filter. If I can invert this so that this one is allowed, except for a certain range, that would be known as a band reject filter, or something called a notch if it's sufficiently narrow. And what did we use to build all of these? What are our components to build all these different kinds of filters? Our building blocks are two different things. What are they again?
Capacitors and inductors.
Capacitors and inductors. Using capacitors and inductors, we can build any of these, which is why capacitors and inductors are the elemental things that are so cool. Okay, if something in your neighbor's home is causing harmful interference to your amateur station, funny story. I consider harmful interference something that blocks my ability to use a frequency which I am legally allowed to use. I had a neighbor who it turns out was 3/4 of a mile away, who was transmitting a signal on 3.525 megahertz, which I thought was really strange because it was FM. I searched for it for 2 years. Every so often I'd hear FM voice on it, which I thought was really weird. I could actually listen. One day I was tuning through and I actually picked up a name and I said, whoa, what? And I went over to their house and it got stronger and stronger and stronger. And I went and asked my wife, hey, do you know this person? They said, yeah, I'll give her a call. And I could hear their phone call on my radio. And it turned out that they were using an old system that used the house wiring to basically duplicate a phone jack in a room that didn't have a phone jack. It essentially would use the house wiring to carry the signals through the house. Well, any piece of wire is also known as a what?
Antenna.
An antenna. So basically they were taking those signals, which were modulated on 3.525 megahertz, which they should have never been, but they were, and they were transmitting it all over the neighborhood. So all their phone calls were being transmitted all over the neighborhood. When we told them that that was happening, I said, this is what's happening. She said, oh my God, I'm disconnecting this thing right now. She disconnected it immediately and I never had a problem again. If something in your neighbor's house is causing harmful interference, work with your neighbor, inform them that the FCC rules prohibit the use of devices that do that, and make sure that your station meets the standards of good amateur practice. In other words, you've built your station properly. What could be a problem if you receive a report that your audio signal through an FM repeater is distorted or unintelligible? Basically, if your battery's running low, you won't be deviating properly. Deviation is basically a measure of how much your FM signal is spreading out. You could be in a bad spot. You could have multipath interference. You could be off frequency. Again, all of these things will cause your signal to not sound right. RF feedback. If RF gets back into your audio circuits, you'll sound all garbled again. If you're told your handheld or mobile transceiver is over deviating, that's basically equivalent to me screaming into the microphone, right? At some point, your microphone and radio are going to lose the ability to have a nice linear response to your voice. If you're screaming into your radio, you will end up with something called flat topping, which will cause your signal to spread too wide on the band. And because nobody's listening for a signal that takes up that much room, part of your voice will disappear as far as they're concerned. And if part of your voice disappears, you sound distorted. All right, we are on to page 90, test instruments and soldering. Okay, a multimeter. All right, so I'm going to bring up a picture of a multimeter, which you guys may have seen at some point. A multimeter is a device that can be used to measure multiple things. So it can measure current, it can measure resistance, it can measure voltage. Those are the three most common things to measure. Okay, so here is a $22 multimeter. Okay. Anyone ever been to Harbor Freight? Harbor Freight's great for certain things. Right. So here's a $22 multimeter. Now, this multimeter might say suitable for use up to 1,000 volts. Would you use a $22 multimeter on a 1,000 volt circuit? Anyone?
Probably only once.
Only once, yeah, if you survived it. Now, for those of you like me who work in higher voltages, has anyone ever seen a multimeter that looked like this? Notice it doesn't look all that different. It's a Fluke 87. A Fluke 87 like this, which measures voltages up to 1,000 volts, right? Looks very similar to that other one, except that this one, when you buy it, is actually suitable for use up to 1,000 volts. And notice instead of $22, it costs $500 each. So basically what you're getting when you do that is that you're ensuring that the meter that you buy is actually suitable for the full range of voltages that you intend to use it on. So a multimeter can be used for measuring voltage. So if I draw a little circuit that has a battery and a resistor, and I want to measure voltage, I would put it in parallel with the battery. Say, okay, well, there's my voltage. Now, if I wanted to measure the current that was flowing through here, I have a couple of options. I would have to put the ammeter, which is an amp meter, in series with the line, which means conceivably I'd have to break it. Or because every piece of wire that's carrying current generates a what, everyone? What does a current make?
Magnetic field.
Magnetic field. I could actually measure the magnetic field. So how would I measure a magnetic field? I would put a coil of wire around this and then figure out how much voltage it made. And this is actually called an inductive ammeter. And what's nice about that is that sometimes you can actually buy that as a clamp, which means you don't have to break your wire altogether. So this is actually an ammeter, even though it shows volts. But basically, this is an ammeter known as an inductive ammeter. Now, in order to test resistance, which is in ohms, I would actually do this and do this. Well, by Ohm's law, what is Ohm's law? E equals I times R. So R is equal to E divided by I. Well, in order to check this, what I would do is I would basically have a test voltage that went through this device under test, and I would measure the current. But what if it was hooked up to a bunch of other stuff first? Wouldn't the current maybe be a little weird? It would. So what I would do before I did this is I would disconnect that device from other things in the circuit, and then I would test it, because in an ohm meter, you basically have a battery that connects across this, and then there's an ammeter that measures the current, and it does the calculation to figure out what the resistance is. Now, this is actually a little bit tricky, because let's say that you have an ohm meter that is now, it's got a battery in it, remember, and you're using it to test a capacitor. What will happen, because this is a positive and negative terminal, is that the capacitor charges up. And then once it's charged up, there's no more current flow because there's no place else for it to go. So when it's first charged, you'll have a lot of current, which means that your resistance is really low. And as it charges up, you'll have a lot of resistance because there's nowhere else for current to go. So it'll look like this. So if you see a resistance that starts really low and goes up basically to infinity, that means that you have a capacitor in the circuit that just charged up, and you're measuring the resistance of a capacitor. Okay, the instrument that you would use to measure electric potential, that's the same as electromotive force, EMF, that's a voltmeter. A voltmeter is connected in parallel. Which of the following can damage a multimeter? If you measure a voltage when using the resistance setting, that'll do it, because the resistance setting actually has a battery in it. So you can actually blow up the battery inside. Which of the following precautions should be used when measuring high voltages? Well, you ensure that, again, the voltmeter and the leads are both suitable for the voltages being measured. Like, I would use one of those Harbor Freight meters to measure 120 volts if I was wearing gloves. I would never, ever use one of them at work to measure 480 because I just wouldn't trust it. I would use my Fluke to measure 480 volts because I know that I've had it for 20 years and it's never failed me, and the leads are in good shape. But I actually do check the leads and make sure that I don't have any cracks or anything like that, so that I'm not going to get a high voltage shock. An ohm meter is placed in parallel with the device because, again, it's actually a voltmeter. It's a voltage source and an ammeter. When you're measuring with an ohm meter, make sure that the circuit is not powered. If you have a capacitor, make sure that, again, you will notice that you start at very low resistance and then it goes up, just like we showed on the graph. And in order to measure current, you measure in series unless you are able to have a clamp-on ammeter. You should avoid, when soldering, something called acid core. Acid core has acid in it. You don't use that for soldering electronics. We use something called rosin core instead. Rosin is a gentle cleaning agent. If you play a stringed instrument, rosin is the same stuff that you put on your bow. The characteristic appearance of a cold solder joint is a rough or lumpy surface. A good solder joint is going to be smooth looking and nice and shiny. Okay, so now we are up to operating procedures. Page 93. What type of amateur station retransmits the signal of an amateur station on a different channel? That's known as a repeater. What type of station can automatically retransmit the signals of other amateur stations? A repeater can do that. There's also an auxiliary station, which is like a forwarding station. So it's basically designed to just hear something and forward it to, let's say, another repeater somewhere. It's just basically goes in, goes out, but nobody's intended to listen to it. That's known as an auxiliary station. There's also something called a space station. Anything 50 kilometers or higher above the Earth's surface falls under the category of space station. So that can be the International Space Station. That can be a really high altitude balloon, although I don't think they can typically get that high. Certain rockets, I guess, if you launch them high enough, can get up to that height. It's about what, 250,000 feet. So that's, no, 150,000 feet. So that's kind of scraping the edge a little bit. But basically 50 kilometers makes it a space station. A linked repeater network. You can have multiple repeaters. We do in Oregon, we have a network of about 50 of them that are all tied together, where if you can get into one repeater, you get into all the repeaters and your signal is retransmitted everywhere in the state, which is really kind of nice. It's a network of repeaters in which signals received by any one of them are repeated by all. So therefore, with a handheld radio, let's say you're all the way on the Oregon coast. If you can get into a repeater there, you can talk to somebody in Portland who's on another repeater, or somebody who's in Idaho, all the way on the other end of the state, or in Northern California, all the way at the southern end of the state.
Is there a way to identify those repeaters?
They're all listed in the repeater books.
So just
And
whatever it says in the book.
Yep, it'll all say in the book, linked system.
Thank you.
And if you then go and look up, because everybody publishes their information, linked system, sometimes there's a code to activate the links. In other words, they're standalone unless you activate the code. Sometimes you have to be a member of a club to activate it. Sometimes they're open for everyone. Depends on how the system builders, because when you think about it, they're all private. It depends how the system builder decided to build it. Common repeater frequency offset on the 2-meter band is plus or minus 600 kilohertz. On the 70 centimeter band, it's plus or minus 5 megahertz. There's also something called CTCSS, which is the continuous tone carrier squelch system. CTCSS. This is also known as TL in the Motorola world, or private line. They are the same thing. Most of the FRS radios, which is Family Radio Service, when you see they'll have 14 channels and 38 sub channels. Those 38 sub channels are actually subaudible tones, which are part of the Motorola system. And what that means is they're not really different frequencies, but what they are is a separate tone that varies from 67 hertz up to 254 hertz that is transmitted along with your voice. And if the other radio is programmed to hear to only receive one and not open the squelch, if it hears something else or nothing, then essentially your radio does not hear and doesn't come alive unless it's got the right signal. So if I say, okay, let's say we're on channel 3 with a tone of 100.0, and I have this radio, it's on channel 3, and it's listening for a tone of 156.7, neither will hear each other. They have to have the same channel, and they have to have the same tone. And that's again known as CTCSS. There's also something called DCS, which is a digital coding squelch system. Basically, if your radio, and we actually have something called the Now What Net, which is a beginner's net here in Eugene. And these are the most common reasons why somebody can't get into our repeater and join the net. They have the wrong offset set, or they have no offset set, so the repeater can't hear them. They have the wrong tone set, so it needs to be 123.0. If they have 100, for instance, from another repeater, it won't work. There's also something called DCS, which is digital code squelch, which is a frequency jumping sequence that is a very small change in frequency, which is supposed to be followed by a particular radio. If it doesn't match, the receiver on the repeater will not listen to it and just ignore it as noise. A reverse function. So we're on page 94. The reverse function on a handheld radio allows you to listen to the other frequency. So remember, we said there's the frequency that you listen on, and there's also when you hit the transmit button, it switches frequencies using the offset. By hitting the reverse button, it flips those. What that allows you to do is listen to other stations that are trying to use the repeater. That's one way that you can diagnose somebody who has the wrong offset, or has or isn't transmitting with the proper tone. You can hear them directly, but basically, if you're not listening for a tone, then you can actually hear them, whereas the repeater can't. So you can listen on a repeater's input frequency. What would cause your FM transmission to be distorted on voice peaks? Well, we get this a lot. If somebody is talking too loudly like this, they're getting really close and talking louder, it gets distorted. Similarly, we get people who, for whatever reason, get used to talking with the radio 6 inches away from their mouth, and they sound like this. They sound like they're barely talking. What we'll say is, you're too far away from the microphone. If they're talking too loudly, we'll say, pull the microphone away from your face. And usually that solves the problem. So let's say that you want to call another station on a repeater. You basically know their call sign. You would give their call sign, like ST2AB. This is N7JI. Over. That's how I would call Abu, by his call sign. If I just want to say that I'm here on a repeater, I would just say, this is N7JI listening, or just simply N7JI monitoring, or just simply N7JI. Just announce that I'm there. Okay. What describes an amateur station that is transmitting and receiving on the same frequency? That is known as simplex. If you're transmitting and receiving on different frequencies, that's known as duplex. Now, when you're on the telephone, if you've noticed that you can hear while you're talking, that's known as full duplex. We don't actually do full duplex. We do something called half duplex, which is where you have different frequencies, but like when I'm transmitting into a handheld radio, I can't hear myself. I can't hear anybody else. So it's actually half duplex. But transmitting on a single frequency, transmitting and receiving, is known as simplex. So we also have these things called band plans. And a band plan is something that is voluntary. And in Oregon, we have something called ORRC, which is the Oregon Repeater Relay Council, or Oregon Region Relay Council. It looks like this. Every region, every state has one of these. So let's say I go to the 2-meter band plan. This basically says that in Oregon, this is how we do things. Again, this is notice that we have on 146.52, it doesn't specifically say, but right here, 14642 to 14660, it says simplex. Right in the middle of that is 146.52. That is a very important frequency to know because that is the de facto simplex frequency all over North America. So the band plan is basically set up to keep people from interfering with each other and getting confused. Certain frequencies are used for repeaters. Certain frequencies are used for simplex. Notice this says Oscar subband. That's satellite. It's orbiting satellite carrying amateur radio. There's another thing that's set up for propagation beacons, general single sideband. Let's just say that if you have single sideband and FM together, they don't play well together. The same thing with CW. EME is Earth, Moon, Earth, or moon bounce. Again, you don't want these groups of people having to fight over frequencies because it never comes out good. HF operation, CQ. CQ means I'm calling somebody, anyone. I'm seeking you, I'm seeking any station.
Question about that regional thing.
Yeah,
So theoretically, wherever we are, we can just do a Google search and say, show me my local regional council.
exactly.
Okay, thank you.
It'll tell you who it is. I don't know who it is there, but I'm sure there is one because every region has one. And all the stations that are eligible for running a repeater elect the insane volunteer who's willing to handle all those arguments and figure out who gets what frequency. So that's called a repeater, or it's called a frequency coordinator. If you're looking for it, that's called a frequency coordinator. Before calling CQ, you need to make sure that there's nobody on a frequency. You need to make sure that you're allowed to be there. Like, let's say you have a technician license and you're on the 20-meter band. You should know that you have no privileges on the 20-meter band. So it's important to know what those frequency charts say. The other thing is you need to actually ask if a frequency is in use. The reason being that as we briefly discussed yesterday, propagation does not always work in both directions. It's also true that propagation between, let's say, Oregon and New York, or Oregon and Florida, I might have a path from Oregon to Florida, but not Oregon to New York. And somebody is in New York talking. I can't hear them. I assume the frequency is empty. Is it really empty? Well, if I start talking and I just start blabbing away and there's somebody in Florida and I have a path between Oregon and Florida on that very same frequency that the person from Florida is listening to someone from New York, I've just interfered with the conversation and I didn't even know that I did it. So then you would ask, is the frequency in use? And that will eliminate those issues. You'll know if the frequency was actually in use, being used by somebody that you couldn't hear. How do you respond to a CQ? Well, CQ, CQ, CQ. This is N7JI. I would answer by saying, N7JI, this is, and then give your call sign. You basically say, I'm calling the station that's calling, and here's who I am. So if I heard ST2AB calling CQ, I'd hear CQ, CQ, ST2AB, Sierra Tango 2 Alpha Bravo, listening. I'd say Sierra Tango 2 Alpha Bravo, this is November 7 Juliet India in Oregon, over. Basically let them know that you're calling them and give your own call sign.
Roger that.
Roger. Okay. Which of the following is required when making on-the-air test transmissions? The one thing we're not allowed to do, with the exception of transmitting signals to a model craft, like a drone or a remote controlled boat on a lake or remote controlled airplane, which we're allowed to do. Those are the only conditions where we don't have to identify the signal that we're sending out. So if I am sending out a signal, just testing out my radio, I have to say N7JI. That makes it legal. So I only have to do that every 10 minutes and at the end of the conversation. So I can transmit test stuff for 9 minutes and then identify it saying N7JI. That just identified all of my communications, even if they're only made in one way format. Q signals, we're on page 98. There's only 2 Q signals of all those we talked about that you have to know. QRM is man-made noise. In other words, somebody is interfering with me. I'm receiving interference from somebody. QRM means I'm getting interfered with. QSY means I'm switching frequencies. Let's QSY to 2 meters. Let's QSY up 10 kilohertz. Let's QSY to another repeater. It means I'm going to change frequencies. A voluntary band plan. A band plan, as we just talked about, is something that the FCC does not do, that we decide to agree upon to keep the peace. So it's a voluntary guideline for using different modes or activities within the same band. So if I were to bring up the band plan, and everybody here has a copy of the band plan, and what I'm going to do is share the band plan. This is the band plan. You will see that within this band plan, on the 2 meter band, for instance, which is 144 to 148, we have Morse code, which is CW, single sideband. It says specifically no FM, and then satellite, and then repeaters, and then digital and simplex and satellites, or sorry, repeaters again, and then more satellites and FM repeaters and FM simplex, with a few exceptions, like for instance, the fact that this red zone exists at the bottom for CW on 6 meters and 2 meters and 1.25 meters. With the exceptions of those, everything else there has been set up by agreements. There is nothing saying the FCC is not saying thou shalt use only these frequencies in this channelized format. Now, if you were to go to Family Radio Service or GMRS, there are certain channels that the FCC has set up for people to use. So if I, for instance, wanted to go to the single sideband section of the 2 meter band, which is this green segment, and notice it goes from 144.1 to 144.3, and I wanted to set my radio dial to 144.2268859. That's perfectly fine. There's no channels. I can set it to anywhere within the band, within the edges, so long as all of my signal goes somewhere inside the bottom edge and the top edge. Same thing on the 10 meter band. If I'm in a band where I'm allowed to go, so let's say we have this thing that says the blue hatch that says novice and technician voice, 28.3 to 28.5. In that blue hatch area, I am allowed to tune to 28.4098265 if I so choose, so long as my entire signal is between the bottom part and the top part. That is a privilege that we have that virtually no other service has. Citizens Band, you have channels. Every other service has channels. We don't have channels.
Can we go back to that picture for a minute?
Sure.
So that's 0.55 spread.
What are we talking about?
How wide is that blue line?
200 kilohertz. It's 28.3 megahertz to 28.5.
Then we have to allow a margin of something to stay away from the edge of the band. Three something we have to leave.
Yep, if you assume that your signal is 3 kilohertz wide, so here's 28.3, and this is where we have to know more, and this is why we're taking this class. We have to know this is 28.500, and we have to know that a single sideband signal is 3 kilohertz wide. And this is 28.500 kilohertz. We know that if the band goes up to 28.500 and we have a 3 kilohertz wide signal, we know that our whole signal has to be inside. So here's the center frequency, and here's our voice signal. What's the highest we can put our dial? 28,497. Because we know that we are on upper sideband, which is on the higher side. And we know that our signal is about 3,000 hertz wide. So this is the absolute highest frequency we can tune our dial to. And that's why it's important to understand all this stuff, because we're allowed all these different privileges that all these other services, they are basically appliance operators, and we are not appliance operators. We actually have to understand what it is that we're doing. We have lots and lots and lots of leeway because of that. But we also have the responsibility of understanding how that leeway works. Okay, who owns a frequency? Anyone? Unless the FCC sets up a frequency that says this is an emergency frequency, like just happened for the hurricanes, stay off unless you're handling emergency traffic. Nobody owns a frequency. So if there's an argument over a frequency, settle it like adults. Okay, now we're on to emergency preparedness. And how about a 5-minute break, everyone? Okay. Cruising right along. Anybody with any questions?
Does
know there
the
must be some.
does the general exam cover the same material in the book?
It's similar, but it's different band edges. So when we start looking at the band plan, the general exam covers, why can't I zoom? Pit height. There we go. The general exam covers all the general band edges. Notice where this says EAG,
Yes.
all the general stuff. So you have to know power levels, you have to know data mode maximum bit rates and stuff like that. But
Is there
go ahead.
is there a preparation material for it?
Yep. The same study guide that I point people to for the tech. There's a book. There's also that same app, the ham radio exam general, which is free. Allows you to practice on just, individual sections of material. And what you'll find is that the basic stuff that you now know, I mean, the basic stuff that you get from the technician license, like I said, I go a lot further than you really need to, because I think that it's important to understand the framework information to make all this stuff make sense. It's very similar to the general license. I mean, the rules and regs are basically very, very similar. It's the specific rules and regs that are specific to the general exam, like the fact that you can be a volunteer examiner as a general. What exams can you give as a general? The answer is you can give a technician exam. You can't give a general exam, but you can give a technician exam. How old do you have to be a volunteer examiner? You have to be 18. Who controls accreditation of volunteer examiners? It's a volunteer examiner coordinator. Stuff like that is on there. Plus, since you have different privileges on HF, you have different modes that you can use. You have different power levels that you can use. You have to know that the 30-meter band has a limit of 200 watts. You have to know that you're allowed on the 60-meter band, 100 watts ERP or 50 watts ERP. You have to know that there's only 5 channels available because we share it as a secondary user with the military. Stuff like that.
All right.
The bit rate, and actually, if you're gonna crush the technician exam, you might as well know, like the bit rate on HF is 300 baud. On 10 meters, it goes up to 1200 baud. Screaming fast, 1200 baud. And then on, I think on 2 meters and up, or 2 meters, it's 2400 baud. And then on, oh heck, what is it? On 70 centimeters and up, it's like 19,200, 19.2K baud. And for those of us who know something about data rates, those are really slow, but they're fast enough to do some stuff with. So, don't expect to be screaming fast data on HF. All right.
Sweet, thank you.
I heard another question. Go ahead.
It's what my soldiers and I like to say. It's good enough for government work.
Yeah. Well, it kind of is. I mean, it's enough to get very rudimentary information across. It's faster than Morse code. Even fast Morse code.
We definitely use bits quite a bit over here.
Mm-hmm. All right, here we go. Amateur Radio Emergency Service. We're on page 99. ARES is a group of, okay, now there are 2 different things. There's ARES and RACES. All right. The only difference between ARES and RACES, they both have the letters ARES in them. What you really have to know is that the fact that C is civil, right? Civil implies that it's governmental. So ARES and RACES are virtually identical, except that ARES, which is the Amateur Radio Emergency Service, is a group of hams that has volunteered for emergency preparedness using radios and people and equipment. RACES are the same group of people that have volunteered for the same kind of service, but with a civil service agency like a government, like emergency preparedness agency within a government. So civil defense, there's that letter C means civil. NCS is a net control station. If you set up a net, that is basically a network of people who are working to do something. The net control station is the person that's in charge of the net and directs all communications within the net. When you participate in a net, unless you're reporting an emergency, you speak only when spoken to, unless you really have something that's important to say. Traffic is information that passes through a network from one person to another or one place to another. So let's say that I was the net control station and I heard that Chris had traffic for Raul, and Chris would say, "This is Chris, I have traffic for Raul." I would take that traffic and I would verify that I got it all right, that every word was right. And I would say, "Raul, I have traffic from Chris." And I'd say, "Here's the traffic." And Raul would say, "Okay, received it all." And then I would get back on and say, "Okay, Chris, message has been received by Raul." So that's basically me operating as an intermediary, verifying that the message made it through and informing both parties. So good traffic handling means you pass the message exactly as it came in. There's something called a check, which is the number of words or word equivalents in a message. Every message also has a preamble. Okay, message 226 sent by Chris at time 13:06 Pacific time for Raul. Here's the message text. That first section is called a preamble. It's basically all the information necessary to pass it from place to place. If you're doing it over voice, for instance, and I say this is for Raul, I spell Romeo Alpha Uniform Lima, because there are a couple different spellings of Raul. It could be Raoul. If I wanted it to be absolutely sure, I would spell out names. I would spell out any strange words that were, uncommon. So use a standard phonetic alphabet. We use the ITU phonetic alphabet: Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, and so on and so on. The check, again, is the number of the total number of words or word equivalents. When do the FCC rules not apply to the operation of an amateur station? The answer is never. Now, the FCC rules also say that if basically all hell is breaking loose and you have a life or death situation, or you have let's say a house is about to go underwater, if you can reach a radio, even if you don't have privileges to use that radio, go ahead and use it. So the rules say follow the rules, except if it's about human life or protection of property. Then you don't have to follow the rules. So technically, you're still following the rules. It's just that after the fact, you might have to explain. Like, for instance, a couple of months ago, there was a forest fire in Idaho. Somebody grabbed a radio and said it was a fire service radio, and he tried to inform the fire department, that was, the Wildland Fire Department, that there was a fire, and here's where here are the location, here are the coordinates that they should focus their efforts. So he was then fined about $38,000 for unauthorized use of the radio, because it wasn't imminent. It wasn't like it was about to burn down his property. It wasn't going to kill him. There was nobody in danger, and he could have just as easily grabbed the phone and made a phone call. But for some reason, he saw fit to grab a fire service radio, which he had no privileges on. He was not part of the fire department, and use their frequencies. So in other words, that's a last resort. It has to be something that's really justifiable. And in this case, it clearly was not. Which amateurs can contact the International Space Station on the VHF bands if you have a technician class license and you're allowed to transmit on the uplink frequency, you're allowed to contact the ISS traveling overhead. A satellite that's operating in mode UV, that's UHF uplink and VHF downlink. It's always uplink downlink. So if it's UV, it's UHF uplink, which is usually 70 centimeters, and 2-meter downlink. It can also operate in mode VV or UU or VU, depending on how they set it up. Okay, so if it's in mode UV, again, that's 70 centimeters up and typically 2 meters down. UHF up, 2 meters down. And this is where it's really important to know, once again, that those band edges that we talked about, remember we did HF, VHF, and UHF. It's important to know which ham bands are in which area and what the limits are on those areas. Everyone, what's HF again? How many megahertz?
3 to 30.
3 to 30.
And VHF is?
30 to
30 to 300.
And UHF is?
300 to
300 to 3 gigahertz.
Exactly. Okay. What mode of transmission is most commonly used by amateur radio satellites? You would think that it's FM, but that's not always true. A lot of satellites are single sideband satellites because you can put a lot more single sideband signals on that band. So satellites use single sideband, they use Morse code, they use data, and they also use FM. The impact of using excessive radiated power on an uplink to a satellite. It basically, if you're transmitting with a lot of power on an uplink to the satellite, you might block other users from ever getting heard. You're basically overwhelming them and they'll never get heard. How to determine whether or not your signal is of the right strength going up to the satellite. Satellites will also, if they're running a repeater on board, will send out a signal. They'll send out something called a beacon, which is here I am, here I am, here I am. Very often there's some data indicating like telemetry, temperature, status of the satellite, etc. They'll also send out a Morse code beacon with their call sign. If your voice, if you can hear yourself, and hopefully you can, if your voice is about the same level as the beacon, that means that you're transmitting with the right amount of power. If they can barely hear you and you can barely hear you, you probably need more. If you're too loud, then you're probably transmitting too loudly and you need to turn down your power. Low Earth orbit is a LEO satellite. LEO stands for low Earth orbit. Anything below about, what do they say? 1,200 miles up is a low Earth orbit satellite. The International Space Station is at about 220 miles. Now, you might remember that yesterday when we were talking about the ionosphere, the F layer of the ionosphere is at about 200 miles. 250 goes up to about 600 miles. So technically, the International Space Station is actually within our atmosphere, which is why certain satellites actually have to correct for atmospheric drag. And that when they say, well, you know, if we have a solar flare, for instance, it can affect satellites. One of the ways that that can happen is that the atmosphere gets distorted and swells up, and you end up with more drag, like from whatever air is still in that area. And that slows a satellite down and can decay its orbit to the point where it then can crash into the ground. A satellite beacon is a transmission, which is a one-way transmission from a satellite that has information about the satellite. Onboard temperature, how high am I, how fast am I going, health and status of a satellite. Who can receive telemetry? Well, anybody can receive anything. You do not need a license to receive, which basically means anybody can receive satellite downlink information. Anybody can listen. Satellite tracking programs. How do you track what's going overhead? You go online or you download a piece of software and you plug in the satellite you want to listen for or look for. And it puts out a map and tells you when a pass is going to start with the satellite going up into the sky and passing overhead. until it disappears. It also will tell you what the Doppler shift is. As it gets closer directly overhead, it basically has no Doppler shift. When it's coming closer, it's a positive shift. When it's going away, it's being stretched out, so it'll be shifted lower frequency. The information needed if you have a new satellite that there's no information for, Johannes Kepler defined laws of planetary motion about 400 years ago. And we use the elements that he created essentially to figure out where a satellite is going to be in its orbit. They're called Keplerian elements. We program them into our program, and it uses those pieces of data and figures out where and when a satellite will be. Doppler shift is an observed frequency change. So again, as something is coming closer, it's Doppler shifted higher. As something is speeding away, it's Doppler shifted lower. And then there's also something called spin fade. Spin fade is when a satellite, because satellites don't just sit there, they rotate, they tumble. As they do that, satellite antennas will go closer and further away. And at some point, the satellite antennas can actually go behind the satellite from you, in which case the satellite spins back around. That's known as spin fade. Okay, operating activities. Operating activity that we're on page 105. Operating activity that involves contacting as many stations as possible during a period. That's known as a contest. It's the activity is actually known as contesting. I am a very frequent participant in contests. I love the competition. I love competing against myself from year to year, seeing how much better I do or how much worse I do this year. Which of the following is a good procedure when making a contact with another station in a contest? So CQ contest, N7JI. Somebody who calls me back, they don't even need to tell me what my call sign is, because I know what my call sign is. If they're calling me, they'll just throw out a call sign. They'll say Sierra Tango 2 Alpha Bravo. I'll say Sierra Tango 2 Alpha Bravo 59. And they'll say, thank you, 59, which is a signal report. And I'll say, thank you, November 7, Juliet India contest. So the goal is to make as many contacts as possible in as short a period of time as possible.
I did it once and I had a sore throat after that.
Oh yeah, it's fun. I've never been able to sit and operate for some of the 48-hour ones. I just can't sit still that long and I'm too busy. But some of them, we have a guy in our club here who we say he's the perpetual recipient of the Iron Butt Award, because he can operate a full 48-hour contest solo without taking any naps.
Oh my God.
Yeah, no breaks, no naps. You know, his wife brings him something to eat and drink, and once in a while he'll go use the bathroom, and that's it. He usually comes up with some amazing scores. He's also got a monster. He's also got a monster station, huge antennas on a hilltop, and nobody else around for miles. So there's very little interference, very little noise.
Are you sure he's a single guy? He doesn't have a twin brother or something?
No, he's Dave. He's KA6BIM. He does not have any. Well, I mean, he might, but he does it himself. That's his thing. Building big antennas and operating in contests. A grid locator. This is one of the things that I sent everybody, if I'm not mistaken, was the grid map. And the grid map is grid square map. There we go. Look, I even have it. And the grid map is the entire world split into rectangles that are 2 degrees in longitude by 1 degree in latitude. Now, this just shows the United States. The other one shows Alaska and Hawaii. But notice that we have letter, and then number. So the letter combination, it starts at the South Pole and the prime meridian, if I'm not, or is it the international date line? International date line, I think. And it goes all the way around from AA up to RW, I think. And so the big letters are 20 degrees in longitude by 10 degrees in latitude. And each of them is broken into 100 smaller squares. And actually each of them is then broken up into 576 even smaller squares. So you can really pinpoint your location on a map. The reason that we do this is that, let's say I'm in Oregon and I'm pointed at Maine. I don't really care. It's not going to be very different if I'm pointed at northern Maine or southern Maine. But let's say I'm pointed at Idaho. Well, it could be northern Idaho, which would be northeast for me, or southern Idaho, which would be southeast. If I just know I'm pointed at Idaho and I have a very narrow beam antenna, that changes where I'm pointing a lot. So if I know that I'm looking for a station in Idaho grid square DN18 versus Idaho grid square DN12, that tells me where to point my antenna. So it's a more granular way of calling out exactly where somebody is on the planet. And that's known as a grid locator. One of the things that's used for locating sources of noise interference, we call this direction finding, sometimes fox hunting or bunny hunting or duck hunting, depending on where you are. We basically go out and we find the hidden transmitter, and we do this for fun. We do this for fun with the hope that we never have to go find a real hidden transmitter, but sometimes we do. Which of the following items would be useful for a hidden transmitter hunt? A directional antenna, something that you can point in one direction. If anyone's ever done any orienteering and you know that you have 3 different points on a map and you think that you're going this way and this way and this way, all of those 3 lines intersect and you know where to go. And that's called triangulation. The IRLP is the Internet Radio Linking Project. IRLP is a way to connect amateur radio systems via the internet using voice over internet protocol. Voice over internet protocol is digital voice communications over the internet. That's exactly what we do when we make a phone call these days. All phone calls are VoIP. When using the Echolink system, I have an Echolink app on my phone. You have to register with the Echolink people and say, I'd like to use Echolink. Here's a copy of my license, because they don't just want any random person popping up on Echolink. Because when you're using Echolink, you actually appear on somebody else's repeater. When you pop out of the ground up into a repeater, it says though you are in that location using the repeater. Echolink, again, allows people using a repeater without actually having a radio. I've been all over the world and used Echolink over an internet connection, which allowed me to check in with my local club, for instance, when I was in South America. I basically just popped up on our repeater during a meeting, and it was like I was there with them, using the internet as a gateway.
I went to a ham meeting this last week. And they were discussing one of the brethren in the club. He apparently does not own a radio at all anymore, for whatever reason. And yet he's active all day, every day, and it's entirely on Echolink. And that the conversation was the naysayers who claimed that ain't radio.
It's not as much
that sort of
radio. I
thing.
mean, yeah, that's not much fun to me. It's more of a utility.
Yeah,
But-
I don't know why he set up that way, but I just thought it was fascinating that in a room full of diehard hams,
Yeah.
they're actually showing some respect to this guy who's gone completely into the Echolink world.
Yeah. How is access to IRLP? IRLP, again, it's Internet Radio Linking Protocol. Typically, you will use DTMF. DTMF is an interesting way to say dual tone multi-frequency. We also call that touch tone. Every handheld radio that has a keypad, people think of this keypad as a way to punch in frequencies. Once you have the push to talk button pressed, you're actually sending out touch tones over the air. And that's how to link one system to another. What type of signaling pair uses pairs of audio tones? Again, DTMF, dual tone multi-frequency. An amateur radio station that connects other amateur stations to the internet is called a gateway. Okay, is everybody ready for rules and regs? Rules and regs. This is the meat and potatoes part that governs what we're allowed to do. Everybody ready? Rules and regs. Okay.
Been holding our breath for 2
Holding
years.
our breath. Here we go. The agency that enforces the rules for the amateur radio service in the United States, and only in the United States, is the Federal Communications Commission, FCC. So why do we exist? Well, if you wonder why we exist and what the rules look like, I can look up FCC Part 97, and those are the rules that govern amateur radio. And I can bring up a copy of the FCC rules. Notice it says Part 97 Amateur Radio Service Rules. For the most updated part, here's a copy of it. So I'm going to open the PDF, and there it is in all its glory. All the FCC rules governing amateur radio. All the pages and pages and pages and pages. And if you have a question, look, there's even the frequencies that we're allowed to use and stuff like that. The answer to why we exist is right at the very beginning. Basis and purpose. Starting right there. We have 5 raisons d'etre. A, B, C, D, and E. You don't have to memorize them, but it's good to know that they exist. This is basically the justification for there being something called amateur radio in the first place. And essentially, this is supposed to be a service, because it is actually an FCC licensed service that is non-commercial, which means we can't make any money at it. And we're supposed to continually train amateur operators. So we're not professionals. We can't make any money unless we're using it for teaching. That is something that allows us to continue experimentation with electronics, with emergency preparedness, with advancement of radio. Because like I said, radio continues to evolve. It is not a dead thing. It is a living thing. It shows up in our lives in many different places that we don't even know. And expansion of the existing reservoir. So by doing this class, this actually is part of Part 97.1D. You're all a part of this. Expansion of the existing reservoir of trained operators, technicians, and electronics experts. So when you go and get your license and then practice and start continuing to learn by operating, you will be participating and doing the bidding that the FCC has basically said that we are supposed to do. So good work, everybody. Okay, let's see.
Thanks to you.
Thank you. Well, and thanks to all of you too. Like I said, this class is not for me. This class is for you. You know, I've been through this before. This class is for your benefit. I happen to learn something as a result of doing it. I really enjoy it, but it's really for all of you. Okay, Part 97, a beacon. A beacon is here I am, here I am, here I am. It's used for, it's a transmitter that's basically sending out information that's designed for one-way communications, for somebody else to listen to and figure out if there's propagation, or to say, okay, well, I'm sending out information saying that I have this 100-watt transmitter in this location. Let me know if you hear me. So observing propagation or related experimental activities. A space station is anything 50 kilometers or higher. And we're on page 109, by the way. When are you allowed to do willful interference? Interference that's accidental is not willful. Willful interference means you're doing it and you know you're doing it. We are never allowed to do this, ever. Which of the following entities recommends transmit and receive channels and other parameters for auxiliary and repeater stations? Okay, here we have again the Volunteer Frequency Coordinator. In Oregon, again, that's the Frequency Coordinator. That is the ORRC. I'm sure there's another one in Illinois. There's a different one in Idaho. There's a different one in Pennsylvania. There's a different one in New York. There might even be one for Long Island, and one for Western New York, and one for Northern New York, and one for what we call upstate, you know, not in the city, but not Buffalo. There might be a separate frequency coordinator for each of those areas. And who selects a frequency coordinator? That unlucky soul who gets to deal with all the arguing people who all want to use a particular frequency pair. That is everyone who's eligible to have a repeater. So if you're a repeater or an auxiliary station owner, you're part of the group that elects the person that figures out who's gonna get what frequencies. Okay, so for the next part, we need to go here. And we go to the band plan. And we're going to look at, okay, what frequency is in the 6 meter amateur band? This is where it's important to know that 6 meters goes from 50 to 54. So we look at those frequencies available, and we see that 52.525 goes into the 6 meter band and the other frequencies don't. What band includes 146.52? We have to know that 2 meters is 144 to 148, and 146.52 falls in between 0.4 and 0.6. Okay, on which bands does a technician class operator have amateur privileges, phone privileges in particular? Well, we look here and we say novice and technician voice. If anyone's curious what a novice license is, it's an unavailable license that existed up until, you could actually get up until about 2007, where that was basically the entry-level license, which was then discontinued and replaced with the technician, which was always available, but you had to start with a novice. So a novice has even fewer privileges than a technician. And so novice and technician voice, we look over here on the 10 meter band and we see that it's again 28.3 to 28.5. So there's the answer. That's actually why we do our Sunday night net on 28.450, because anybody with a technician license or higher can operate and join our net. Where can single sideband phone be used on 50 megahertz and higher? Well, you'll see that single sideband, that's also known as phone. Phone means voice, like telephony. That's the light green. You will see that there is a section on every band that is set aside for that mode. And that is typically used for weak signal work. So long distance communications, strange operating modes, things like that. What bands are operated to Morse code only? You will notice that on 6 meters and 2 meters and 1.25 meters, that there are these red sections. Those are Morse code only. So of those choices, you will see that the answer that is correct is on 6 meters and 2 meters, 50 to 50.1 and 144 to 144.1. Those are set aside for Morse code. We also have a kind of a weird band that isn't even shown here. Notice that 1.25 meters goes from 222 up to 225. We also have a separate section of this from 219 to 220, which is set up for fixed digital messaging systems only. Fixed digital, they call it fixed digital message forwarding systems only. Basically, these are like store and forward bulletin board systems, and it's only digital. It's important to know that exists. I don't know anybody who uses it, but legally we have to know that it exists. And Vic, why should you never set your transmit frequency exactly at the edge of an amateur band?
Because your frequency is 300 something wide kilohertz, 300 kilohertz wide.
3
kilohertz.
3 kilohertz.
Say it again.
3 kilohertz.
3 kilohertz wide, and you don't want your fat self to fall over the edge,
right?
Because then you are out of band and you get a nasty gram from the FCC or some volunteer policeman.
Correct. That's why and in addition to that, there's no guarantee that your frequency display is exactly accurate. So
Which is probably the more important point.
Yeah, and also because your transmitter will heat up as you transmit, the frequency might drift a little bit, which means that what you thought was in band is now suddenly slightly out of band. How are amateurs restricted in segments of bands where the amateur radio service is secondary? Notice that we have this on 70 centimeters. This says 420 to 430, not available along Canadian corridor. Any idea why? I believe it's about 100 miles within the Canadian border, of the Canadian border.
Canada has their own FCC agency and they control all of that border.
Yep.
Including
In
US
fact,
territory.
In fact, 420 to 430 is not part of the Canadian ham band. And this is actually used by the Canadian military and other services, which basically means if we're within 100 miles of the border, they don't want you using it because you might cause interference with them. And actually, interestingly, 420 to 450 as a ham band, we are actually secondary to the military. We are not the primary users of that huge band. We are a secondary user, which basically means if the primary user says we really need to use it, we need you guys to shut up, we have to shut up because we're secondary. Okay, except for some specific restrictions, what is the maximum peak envelope power for technicians above 30 megahertz? Well, here's 30 megahertz. That's the end of HF. So we're basically looking at all of these bands. How much power are you allowed to run? That would be 1500 watts. 1500 watts, and it's PEP, which is peak envelope power. On any HF band where you have privileges, notice that it's the blue or green hatches down here. You're allowed to run 200 watts, which is actually a lot. I don't even have a 200 watt transmitter. License classes. Okay. Moving right along. What license classes can you get now? You can get a technician, you can get a general, and you can get an extra, known as amateur extra. Don't know why it's called that, but it's called an amateur extra. The term for a license is 10 years. And when are you allowed to operate? Basically, if the license shows up in the FCC database, you're allowed to use it. Interestingly, you won't even get anything on paper anymore. The FCC used to mail out licenses. They don't even do that anymore. If it shows up in the database and it says active, you're allowed to use your license. So what proves that the FCC has issued a license? If it appears in the FCC ULS database and says active, it's a license and you're allowed to use it. Who can select a call sign under the vanity call sign rules? That would be anybody who has a license. What's a valid technician call sign class format? Okay, so United States call signs have to begin with W or N or K or AA through AL. Typically, AA through AL are limited to extra and advanced. You can't get an advanced license anymore. So basically, you're as a technician, you will get something with a W, an N, or a K. Now, every call sign has one number in it, depending on where you live, 0 through 9. It will have, before that number, 1 or 2 letters. And after it, it will have 1, 2, or 3 letters. If it has 2 and 3, this is called a 2x3 call sign. If your call sign is, for instance, W7ABC, that is a 1x3. Any technician class operator is eligible to get a 2x3 or a 1x3. That's the simple rule. So the question is, can you get W1XX? And the answer is no, because that's a 1x2. That's an extra class call only. Could you get like KA3ABC? That's a 2x3. And that would be valid. What's the grace period after your license expires? If you let it expire for whatever reason, you have a grace period of 2 years where you can get it back. Are you allowed to transmit during the grace period? It'll say in the database expired, which means you are not allowed to use it. until you re-up your license. And it says it changes state from expired to active. Once it's active, you can use it again. What defines a club? A club has to have at least 4 members. The thought being that 4 members would be the officers of the club. So if you desire to create a club, you have to have 4 people, and you actually have to have a constitution. Let's see what can result in the revocation of a license. And that would be if the FCC tries to mail something to you and they can't find you. Let's say it comes back as undeliverable. The FCC can actually pull your license. From what locations can an FCC licensed station transmit? That would be anywhere in the United States, or from any vessel or craft located in international waters and documented as registered in the United States. So if I have an American flagged cruise ship that I'm on, legally, I'm allowed to operate there as if I'm in the United States. And I would have to ask the captain, am I allowed to operate? And the captain may say no, the captain may say yes, but legally you're allowed to. Okay, what are the restrictions concerning language? Indecent or obscene language, basically those 7 dirty words that George Carlin once talked about, those are prohibited. The same way that they're prohibited on commercial airwaves, they are prohibited on the amateur bands. And you can get fined the same way. Those fines can be pretty big, so don't do it. I actually have off-air Scott and on-air Scott, and we have somewhat different vocabularies. Under what conditions is an amateur station authorized to transmit music? There's only one: when it's incidental to an authorized retransmission of a manned spacecraft communications. This rule exists because the space shuttle, as it was flying overhead, used to have space shuttle retransmission, and they would wake up the astronauts with music. So in the process of waking them up, they would transmit music to wake them up, and that would be rebroadcast. So they made a rule that said that you're allowed to do it only then. When are we allowed to transmit messages that are encoded to obscure their meaning? Only if you're running a radio controlled craft, again, like a drone, or a remote controlled aircraft or remote controlled car over a long distance, and you don't want it to crash, you don't want anybody to take it over, or when you're transmitting space commands, because nobody wants somebody else to take over a satellite and redirect it into the ground. So, in only those 2 cases, you're allowed to do it. We are allowed to contact hams anywhere, unless their agency, their ITU representative, which is the International Telecommunications Union, has said, we don't want your hams talking to our people. There are very few instances that this is true. We're still allowed to talk to Russian hams. We're allowed to talk to North Korean hams, if in fact there are any, which there aren't. When can somebody receive compensation for being a ham and operating on the bands? The only time you're really allowed to do so is if you are a teacher and you're using ham radio as part of your curriculum. You can still get paid for being a teacher. When are you allowed to sell something on the air? Basically, if you are doing it once in a while and it has something to do with radio. For instance, if I am, let's say, we have a swap net on the air here. If I'm selling a handheld radio, not if I'm importing handheld radios and selling them, but if I'm selling a handheld radio, I can say, I'm selling a radio for $200. Please contact me. That's okay. Broadcasting is a transmission intended for the general public. This is different from a one-way transmission. A one-way transmission is designed to be sent to other hams. So it's like a broadcast, but a broadcast is literally sent to everyone for their general use. A one-way transmission is like a broadcast, but it's intended for hams. So what is a one-way transmission? Well, that could be sending out code practice. That could be sending out an informational bulletin from the ARRL, indicating that there's a special event happening, things like that. When are we allowed to support broadcasters? So for instance, like, when are we actually allowed to send information out for the general public? And that's when there is news gathering or program production and things like that. And this is one of those special areas where if there's a bona fide emergency and people are either going to die or there's like a dam that bursts and it's going to flood a town, that would be an imminent hazard to property. So in that instance, we would be allowed to use our radios and our frequencies to protect people and protect property. So what are we allowed to actually say on the radio? Well, we're allowed to do communications incidental to the purposes of the amateur radio service. That purpose, there were 5 of them right at the very beginning of the rules, and remarks of a personal character. In my case, I used to laugh about the fact that people would talk about the fact that their back really hurt or that they'd have to go to the doctor tomorrow to get a blood test. Well, that has become me as an older adult now because I'm 53 and my back hurts and sometimes my leg hurts. And, we talk about that stuff. And I used to laugh about it. And I'm sure that the younger ones of you will laugh at people when you hear them on the air. And just remember, someday that will be you. Okay, so now we have on page 118, the difference between a control operator and a station. Okay, a station is a pile of equipment. This is an amateur radio station. What we saw at JD's shack, that's a station. A station has no privileges to operate. A station must be operated by a control operator who is responsible for it. So when I grab this, I am the owner of this station, and when I push the button, I am the control operator. I am responsible for what goes into the microphone. A station can never operate without a control operator. So if there is a station that has a control operator, or that has an owner, like a station owner, like a club, and I am the control operator, we are actually both responsible for what comes out of it. So the equipment owner and the person who is functioning as the operator are both responsible for what comes out of it, like if something malfunctions. If a repeater inadvertently retransmits communications that violates the FCC rules, somebody gets on the repeater without a license and starts cursing, which does happen once in a while because people are people, and some people, for some reason, decide that they're going to do stuff like that because they think it's funny or they have a grudge against somebody. The person that owns the repeater is not responsible for shutting down the repeater. Although they may feel an obligation to do so, they're not legally responsible for it. It is the originating station that has decided to do that. You are only, let's say that I walk into a club station that has no privileges at all, because stations themselves don't have privileges. Only the operator has privileges. The person who owns the station has an extra class license, but isn't there. I have a technician class license. I walk into the station, and if I'm the control operator, my privileges convey to the station, which means that even though I have a technician class license, I might think that it could operate because the owner has an extra class license, that extra class license would apply. Well, it doesn't. The control operator's privileges apply. So a technician class operator, unless there's an extra class operator present, cannot suddenly start operating like an extra class licensee. Any station, anybody that has a ham license that's allowed to transmit on a frequency that's used for a satellite uplink can appear on the satellite, even if it's transmitted on a frequency that you don't have privileges for. So your voice is being moved somewhere where you don't have privileges. That's actually okay because you didn't break any rules getting your signal there. Control point is the point at which the control operator function is performed. So in this case, this is the control point. This is local control. I have my finger on the push to talk button. There's also something called remote control. Remote control, for instance, is operating a station over the internet. If I'm operating a station over the internet, I have to physically be present at the computer that's doing the control. I would basically indirectly operate the station controls. Automatic control, a repeater is automatic because there's nobody physically sitting there operating it. Somebody has to be responsible for that repeater, and that would be the repeater owner. But again, if somebody else uses it illegally, that's not their fault. Okay, we are, I believe, on the very last part. Yes, we are. Yay. We're going to make it. Okay, do we have any questions? I know this is a lot of information so far, but do we have any questions?
I have a question about the Canadian border.
Yep.
Take me back to that. Was something about limitations on us?
There's a map. If you look up, what's it called? The Canadian corridor. And it's an exclusion for the 70 centimeter band along the Canadian corridor. And that's basically because between 420 and 430 megahertz, Canadians don't have a ham band there. And they are used for, those frequencies are used for other things. And they figure that outside of this area known as the Canadian corridor, which I think is about, I think it's 100 miles, 100 miles or nearer to the border, but I'm not 100% sure. You're not allowed to use that range of frequencies because you might interfere with other services that are in Canada.
Okay, so it's just 70 centimeters.
Yes.
The rest of it's wide open.
Yes.
Okay, thank you.
Let's see, 420 to 430. Here we go. 420 to 430 Canadian corridor. Canadian fixed and mobile services. And in fact, here's the, if you're really curious, here are the rules of the Canadian government. That's Department of Communications in Canada. And here's arrangements with the United States. So this is all the rules in and used for radio location, et cetera, et cetera, et cetera, et cetera. If you really want to get into it, apparently the Canadian rule book is really chock full of information. And I'm sure there's equivalent information in the United States. Okay, here we go. We are on page 121. When are you required to transmit your call sign? You are not required to transmit your call sign when you start talking, although most people do. The requirement is you're required at least every 10 minutes during the conversation and at the end of communication. So basically you're having a talk with somebody, you can just get on and start talking so long as you ID within 10 minutes. Most people like to use their call sign. Go ahead and do it. It's safer that way. When are you allowed to transmit without identifying on the air? When you're running a radio controlled craft. So drones or a remote controlled vehicle or something like that. What language can you use when operating in a phone subband? You can use any language you want. I have had many conversations in Spanish and a few in French. If you're in the United States, you have to identify in English. You have to give your call sign in English. You can have the conversation completely in Swedish, but you have to give your call sign in English. When I was in Chile and Uruguay, I had to identify, even if I was speaking English, I had to identify in Espanol. Noviembre 7, Cota India, Diagonal Charlie Echo 5. I had to give my ID in Spanish because that was the rules of the country I was in. Okay, how do you identify a station? You send your call sign using Morse code or using a phone emission. Phone emission is otherwise known as your voice. What about the phonetic alphabet? It's encouraged. People like it when you use the phonetic alphabet. It's confusing when you use a different phonetic alphabet. So if I'm spelling the name Hudgens, it'd be Hotel Uniform Delta Golf India November Sierra. So for those of you who are in the military or work for the police or the fire department, this may prove a little bit confusing because Adam, Mary, David, right? We don't use those. So occasionally, like I have a friend who was a police officer, he will break into his Adam, Mary, Boy, David phonetics. It's okay, but we prefer to use the ITU phonetics on the air. Let's say that you're operating as a tactical station. So you're doing support for a road race. How do you identify your station? Race headquarters. Aid station 6. How often do you have to use your real call sign? Everyone?
Every 10 minutes.
Every 10 minutes and
at the end of
at the end. Exactly the same rules. You can call yourself anything you want, but you still have to give your real call sign every 10 minutes because those are the rules. A self-assigned indicator. So let's say that I am N7JI and I am operating in Tennessee. So that would be I'm /W4 or I'm slant W4 or stroke W4 or /kilo 4 or stroke November 4 or /4. Those are all self-assigned indicators. And I can either do I'd say the word slash or slant or stroke. Those are all valid for a self-assigned indicator, which basically means that you're not required to do it, but you're doing it anyway to indicate that you're somewhere else. Third-party communications, that's a message from a control operator to another station on behalf of another person. So let's say that I'm talking with another ham. I'm the first party. They're the second party. Anybody else who we're passing messages for becomes known as a third party. We do not have third-party agreements with every other country. Within the United States and Canada, anyone can talk to anybody. But with regard to other countries, you actually have to look up the rules and see whether or not we have third-party agreements with them. The reason for that is that in a lot of countries, the government owned the phone company. And why would the government allow people to circumvent their own phone company and take money out of the government's pocket by allowing people to basically bypass it? So that's why certain countries don't allow it. And if somebody comes and knocks on your door at 3 a.m. and says, we're from the FCC, we'd like to inspect your station, we think that you're interfering with air traffic control at the nearby airport. What do you have to do?
Ask them for their credentials first.
Yep, ask them for credentials, and they say, yep, we're really from the FCC. We really need to see your station. You let them in. Yep.
Yeah, you have to comply.
You have to comply. And if they say, yep, you're interfering, you're not going to get fined, but you need to not operate until you figure this out. Well, that means, the FCC told you need to comply and not operate until you figure this out. So you need to not operate until you figure it out. And that's when you start asking people for help and things like that so that you can comply, or you figure out what transmitter wasn't working right and you figure out what the problem was. Well, that's the end of it. That's everything. How's everybody holding up?
Pretty good.
Pretty good. Okay.
Good, man.
I'm developing a lot more confidence than I had yesterday morning. So
that's excellent.
Good. Thank you very much.
Starting to go a little batty.
Yep. Well, for those of you who are getting ready to take an exam, I'll see you over there. Does anybody have any other questions?
Kind of a sideline question.
A sideline.
In regards to the video, you'll be uploading again and sending us the link?
I will.
That would be fantastic.
I'm going to see if my daughter is there for the exam. All right. Any other questions? Last chance. I appreciate everybody being here. It,
I'm sorry, is the exam on a different Zoom or are you going to call?
oh, no, different, totally different. If you're signed up for an exam, the part of it is that we're going to send you a link to the room and we
Email that?
will, yep, you will sign in from there. You have two devices. You have your computer and you have a phone or an iPad or something like that. So that one of them is a computer with a camera so we can see what, we can see your face. And the other one is an auxiliary camera so we can see the whole area.
Is that the Zoom link that's in the remote testing agreement form?
I'm not sure, probably. But for all of you who are taking an exam, don't sign in yet until you, well, let's see. Let me see. Until you are asked to sign in. So I just got a note and I don't know what that said. Okay. Well, if there's nothing else, we'll see you over there. And so long as I've got good phone numbers for everybody, we're going to start calling and let you know. And I'll see you guys over there. And if I'm not going to see you today, until next time. And let me know how you're doing and how the studies are going. And if you have any questions, feel free to ask.
Thanks, Scott.
73, and thank you very much.
Thank you all.
Thank you so much again.
You bet.